Alrighty, I am working on my SAT solver today, and we were just having, before I started recording here, a little talk about what I'm planning on doing. But the main goal for today is this block in my to-do list right here, the usage features. So I want the ability, right, if you recall, I think I showed this on stream last time, I can run my solver now and it generates a Sudoku board. So I've got the Sudoku rules encoded into my formula, and then I don't have any numbers plugged into the grid, so it's like an empty Sudoku board, and the SAT solver basically proves that it is possible to find at least one valid Sudoku board by doing it. It finds one, and then we translate from, these ones and negative ones up here are the output of the solver, and we translate that into the Sudoku grid right here, right? So we know it can generate a Sudoku board pretty much instantaneously, but that's on an empty board. So what I want to do today is be able to plug in some fixed values. So once I have all of my assignment or my formula that like structures the problem, I want to be able to fix certain variables and say these need to be these numbers or something like that, and let it try to solve a real problem, like a real Sudoku board with actual constraints in it, and see if that is still fast or if that starts to make it harder. Because it might be that with real constraints, it can't just cruise through and make good guesses the whole time, but maybe it can. Maybe it will be relatively easy for it to solve solvable Sudoku boards just in general. But then the other thing to do here is, if you look at the way I write the constraints for Sudoku right now, it takes 1, 2, 3, 4 big paragraphs to write all of the constraints. And that's not bad, given that like this is a reusable structure that can be used for all kinds of constraint problems. The fact that you can specify Sudoku in total like 130 lines is not bad. But I think it could get better. And so I want to spend some time just looking at the most common patterns popping out here, and maybe some common patterns that I can think of, and writing some better APIs for structuring constraints at a higher level. So yeah, that is what we're going to do today. Good morning, Piggy Bank Studios. Let's start with this first one, fixing some variable assignments. So in order to do that, so there's a couple ways we could do it, right? One very easy way would be to add in, so to fix a variable, what you could do is, remember, it's a CNF structure. So it's like a bunch of these things called clauses, which are basically lists of variables, and it's just a bunch of these things. Some of them have knots on them, right? Right, it looks like stuff like this. Okay, and this is the structure. So if I wanted to say, hey, I really want x1 to be true, I could just put this in. So remember, the clauses are ORed together, or like the internal literals of the clause are like ORs in a Boolean formula, and then between clauses it's like ands, right? So if I put in a clause with a single variable, it's like saying I have all of these things, so these all have to be true. Oh, and x1 has to be true just because I put a clause in there with that literal by itself. So that's one way I could do it, and then the solver would be forced to make that work. There's a couple reasons why I don't like doing it that way. So let's talk about the other option and then pros and cons. So the other option is option number 2 is that after we have our formula, right, let's just call this formula, and option number 2 is that after we have our formula, we have this thing called a model. And the model is like the list of what variables, how we've assigned the variables, like what assignments we've made to the variables so far. I don't really love that name, but it's from the literature. I kind of want to do a renaming pass. So let me just, as an aside here, when I'm building something like this, I have an interesting choice. I can either exactly replicate the jargon from the literature. I could completely invent my own jargon and try to come up with something that sounds um, less like hardcore math nerd stuff and more like programmery stuff. Like a lot of stuff here we talk about like models, assignments, clauses, um, uh, conflicts. They're terms, but they're so dense. They're in such narrow terms that you really have to read how you solve SAT problems and what a CDCL solver is to know the terms. They are not terms that teach the topic on their own. So I could try to switch to coming up with ways to describe all of the things with terms that are a little closer to automatically implying the right thing. Or I could land somewhere on a spectrum between those. There might be other ways I could go about it. I could, obfuscate as much as possible, I suppose, as well. But I'm not really sure which way I should go. I don't know if I should go with make this match literature so that people who look at it will have a road into the literature, or if I should make it not match literature so that people who are never going to be comfortable with the dense jargon might have a chance at learning how to do SAT solvers, right? So there's kind of like pros and cons on both sides, and I'm really torn, but I've been leaning away from using existing jargon and more pushing the needle more towards the side of renaming things. But I'd love to hear what other people think about this issue. Like, would it be a bad idea to rename things in order to kind of make the topic approachable to people who would otherwise never learn it? Or should I try to stick with the tradition? Felipe Code suggests jargon plus a comment with Wikipedia links. That's not a bad idea, although I'm afraid that just kind of leans into it's not like, I don't know if that makes it more learnable to people who don't already find it approachable, you know. Like I have the impression with something like this that it's something that could be put in the hands of more people if it sounded and felt more concrete. If it wasn't built out of such abstract symbological concepts, and it was more like immediately relatable on a visceral level. Maybe. Anyway, we're gonna go with the word model for now because I don't have an alternative for this anyways. Yeah, it's true. It might be hard to name some of these things in a way that actually makes any difference. Um, yeah. Piggy Bank Studio says, I'm still partial to finding an analogy that gives you a bunch of words. That could be good. Gotcha. Um, anyway, thanks for your feedback on the topic. This is just something I've been wondering about if I make more confusion or if I actually help by coming up with my own names that because I feel that I at least can pick names that make sense to me, and then there's a question of like, do the names that make sense to me actually help? So maybe what I need is to have people who don't know as much about SAT review my naming schemes before I publish it, like as a usable library or as a educational material or something. Get a little play testing on my terminology or something. So what happens in a model, getting back to this, is a model, I'm going to kind of make like a pretend syntax for it. We have these things called like decision levels in the jargon, or in my naming scheme, guesses. And guess 0 has a special status, which is that guess 0 cannot be undone. when we are going to, like, let's say, like, the assignments look like this, right? It's basically a list of assignments, which means a list of places where we set a variable in the formula. So the formula has some variables. We set them to true or false, right? Those are the assignments, and then they happen in these sequences, or in these, like, tiers that I call guesses. And what's interesting is that, guess 1 here represents the first guess that we made while trying to solve the problem. And so on and so on, right? And they can then have additional things in them. But whenever we roll back, if I say roll back to guess 1, what that means is we would roll back everything to, like, this, right? So we would say, like, say there were a bunch of these, and I say go back to guess 1. Well, it would be like this. It would keep what we had for guess 1, and it could continue from here, or it could make a guess from there, which means you can never actually roll back to before 0. But that's on purpose, because guess 0 is where we put down things like deduction. So if my formula would look like this, formula and x1, and then I didn't do anything to the model, I start with a blank model, then before it makes any guesses, it's going to deduce x1 has to be true, and so guess 0 is immediately going to contain that x1 equals true, because it can deduce that, right? So in this case, if this was my formula, it would put this here because it cannot be any other way. And so I have an option now to say, well, instead of putting it here, what if we just assign some variables in the model at guess level 0 before the solver runs? Then we don't have to modify our formula, and we can reuse the formula. And it's just a matter of mutating the model. And another thing that I do like about this is, in order for it to, if I do it this way, right, up here, then it basically has to reconstruct the same thing. It reconstructs the situation where this model has guess 0 containing x1 equals true, but it has to do that by thinking. It has to go through the formula and find them. If I just assign them directly in my API, instead of modifying the formula in my API, I kind of short circuit that part of the problem. So I think this is the better way to do it. The only problem is I don't have any API exposure for the model right now. So okay, so let's try to do this. We need to figure out how we're going to make an API for that. So here I build the constraints. Oh, and there's another thing. Let's go back to scratch. There's another thing I want to talk about. There's an option 3 here. So the formula, these are the CNF formulas, right? Assign variables inside the model before running the solver. The third option is we have our SAT formula. So here I build the constraints, I call them, but it's just the free SAT. It can do ands and ors and nots in any order. There's no conjunctive normal form yet. And then we convert to CNF. What we could do is we could take that plus a assignment list and simplify the SAT formula before we make the CNF formula. So here's some pros and cons of this option. The pros are it can actually simplify the input data structure, right? So the SAT solver is then being asked to solve a simpler problem. Like we can maybe reduce some clauses down in size, maybe eliminate some clauses. depending on how many things we fixed, it could make a dramatic size change. And then we can also shift that up into the SAT level instead of doing it right on the CNF level. So we could do something like, say, if we look at the Sudoku case, the Sudoku case has the rule that there is there's each cell, there are 9 possible things that can go into it. So the numbers, 0 through 9, N2 is my 3 squared. So a 3 by 3, like a rank 3 board has 9 possible cell values, right, in Sudoku. And so I'm going through 1 through 9 here, actually 0 through 8, but conceptually 1 through 9. And each one of those is a variable, and I'm saying one of them has to be true. So I'm ORing together each of these possible states that the cell can have. And then I'm pairwise saying it cannot be both. So I take 2 of them, VI and VJ. I make the thing that says, okay, both of them at the same time. And then I say cannot have both of them at the same time. And I AND all of those together. So I have a new rule at the end that says one of them has to be true, but it cannot be the case that 2 of them are true. So I get a constraint that says exactly 1 is true. What would then happen if I went in here and picked one? Like I have a square and I say, well, there's a 3 here. Well, I would set one of these variables to true. I would then be able to, from the level of the SAT formula, say, oh, this clause is true because there's a true thing in it already. The whole thing is true. And this, all the spots where there can't both be true will just fill in the fact that all of these are false right away, and we would eliminate an entire cell's worth of logic structures, right? We would just zap it all away just by applying the simplification here at the SAT formula level. So that is kind of interesting, but it's a lot harder. And it has the downside that your formula changes every time you change the assignment. So if I start with a CNF formula that's my Sudoku CNF formula, and I want to run it on multiple boards, then I can just make these assignment lists basically and hand them to the solver. If I do it this way, then I make my SAT formula, and then I make my assignment list, and then I have to do the conversion every time. Now, maybe that's fine, but you can see how it's a little bit more work, right? It might also kind of obscure things, like if your formula is changing under this method, your formula changes as you change the assignments, and so what you were expecting to see is like, oh, this variable number here corresponds to this cell, but that stops being true because variables get eliminated and sort of cleared out from the problem, and so there's no longer a clean mapping from variable indexes to your space, which I think is a pretty compelling reason to maybe not do it. At least not right now. There's some reasons why you might want to do this if you want to go as fast as possible on certain cases, but I think that the right balance for now is still this one. So yeah, so let's make a block here where we fix build fixed assignments. Maybe I'll do this up here, build the fixed assignments. And now the question is, I think for an API, I'll just separate this from, I'll separate the API for specifying your assignments from the actual implementation detail for now. And I'll do that this way. So we'll just build, a chain of these things. What do I want to call the separation here? Okay. So we'll have a first, last, and a count here, right? And I'm trying to think if I want to detect like double assignments. Like if I fix a variable twice, it would be nice if it caught that as soon as possible, but it will take extra work to do that. Well, there are two different ways I can do the extra work. I can scan the whole list of nodes and see if I already have the variable, or I can create an array of Booleans that mark whether or not we've assigned a variable. And that way it'll go fast, but it'll mean you have to allocate this extra memory that's I could also put that memory in a separate block and actually discard it, so it doesn't have to be permanent, which would be nice. So that could look like this. And then you would go like, okay. So we already have a scratch, which is fine. Nah, this is just a lot. Let's just do it slow. For now, yeah. Let's see, FATSAT. Yeah. This is good. This is fine. So we'll do it like this. Well, I'll do that for later. So we start one right there, and then we need the ability to mark certain variables. So let's say I was going to set I'm going to do a quick renaming here. If I don't want fixed, I want fix. Fix node. Fix vars. Fix vars. Again. Let's see. Okay, so right now it generates a 1 in the top left cell. Let's just give it one new constraint. Let's say the top right cell is going to be the 1. And see how it deals with that. So in order to do that, I need to remember how I index. So that is going to be variable number. I'm going to need the Sudoku rank n2, okay, n2 times x plus n2 times y, where in this case x is 8, y is 0, so we get that, and then it's plus 0 for the cell having the value 1, so there we go. And I'm going to fix that to true. I'm going to fix that to have the value 1. All right. And then if that is good, then we build the formula unaffected by this for now. We could use this fixed data structure to simplify our SAT first and then build the formula, but we don't have that. We're not doing that right now. Instead, we're going to take that fix and we're going to put it right into the solver. So the CDCL solver is going to take a fix vars. That'll be fine for now. This might want to evolve at some point to a situation where we initialize a solver, set some parameters on it separately so that, like, if this ends up being a parameter list with 5 different things the user can configure, then I'm starting to feel like, hey, instead of passing all of the parameters as a function, why don't we create a solver instance, set its state up, and then run the solver as a sort of control API. But there you go, you get your fix values, and then okay, so our SAT formula looks like that. Our fixed variables becomes another part of the constraints layer. The constraints layer is kind of the layer the user interacts with. In my mind, the constraints layer is the layer the user interacts with to build the constraints of their problem. This is the API for constructing constraints. Con there, I guess I was imagining it meaning constraint initially, but it could even mean construct. This is the construction of the problem section. So we need a FATSAT con fix vars new. That goes on in arena. And we need a function FATSAT con fix, I think was the name of the other one. That's going to need to take the arena, the fix vars, the variable, and the value. Okay, so this guy's easy enough. We just push one of those on and return. We're not doing anything right now when we construct it that's special, but we might later want to build that map of booleans to check for duplicates. For now, we're just doing it the slowest way. By the slowest way, what I mean is let's do it like this. What I mean is we iterate the existing fixes. If any of them have the same variable as the one we're trying to assign, then we grab it. So if we get a match and the match is a conflict, then we're going to emit an error. Okay. Now, if no match, save a new fixed node. So if we happen to set the same variable the same way twice, then we'll notice that we had a match and we just won't generate anything. We won't generate an error, we won't generate another node. If we have a conflict at any point, we'll emit an error saying, hey, this looks bad. And if there's no match, then we have to make one, right? We have to make a new node. So in that case, we go like node equals push an array onto the arena for a new node. Queue up that node on the chain and fill in the values there. So there we go. We should now be able to construct this data structure that represents the way we fix variables. Now the question is, can we use it? Okay, so right now, nothing has changed because even though I've constructed it and passed it into the CDCL solver just ignores it. So what we want to do is here, when we make the CDCL, right, the first thing it does, well, after we've constructed it, is it goes into propagation. But I think what we want to do now is say, okay, if you have fixed variables, then the first thing you need to do is you need to let me see here. I'm going to move solution up a level like that. And we're going to say right here, assign fixed variables, right? And so this is just a walk over the fixed nodes. And somewhere in here, we have like a function for making an assignment, right? Yes. So we should be able to just say all of these get assigned. Here's the CDCL. Here's the variable. Now our values aren't in line with each other. Let me change that for now. So val equals val needs to change. It's going to be if val. Oh, but that's not good. Okay. All right. We'll do it like this. I want to rearrange how I do those soon, but that should be good. So we're using 1 for true and -1 for false. this can be like this: val equals 1 or val equals -1. Right, those are the things you're allowed to set as a fixed value. Okay, so when we are assigning, we pass a deduction clause, no deduction clause. These are just fixed values. They are not being deduced. So now, when I run, what happens? Nice! Look at that. It put the 1 right here. Neat idea, Brett. I'm glad that you have. Brett is suggesting a sort of science fiction story about SAT solvers where the SAT solver gets used um, to analyze someone's mind sort of diagnostically and figure out the logic of their uh, trauma, right? And I don't know if that's a realistic use of a SAT solver or not, because I don't know enough about the psychology principles that would have to be true to make that work. But is exactly why I like doing stuff like this. It seems to me very important that we start translating really cool the jargon and utility of really cool tools outside of their little bubbles and exposing them to other fields where creative ideas of how they might be applied can be spotted, right? The people who are great at writing SAT solvers might not be the people who are great at spotting the most valuable places to use them. And I think we can see this if we look at where SAT solvers get used. They get used in like theorem proving, compiler optimizing. They also get used in some other more practical, like cryptography, I think is a slightly more creative, like security stuff is a slightly more creative kind of use case, but still kind of in the same vein. Are we sure that these are the only use cases? How would we know if there was a use case that came from a field that was so non-computery? If you have to be a computer wizard to even get SAT in the first place, how would you ever notice that it's applicable to a super deep problem in a different space? And the answer is we have to take as much and to do as much effort as we can to translate out these cool tools into other languages, other ways for them to be understood, so that hopefully cross-pollination can happen and new ideas can be explored. All right, so I can fix a 1 right there and it solves, right? And it puts the 1 there, and we can go back and say like, where did I do that? FATSAT test 1. If I take this out and do nothing in here, then it should be generating, yeah, the 1 with the 9 here and the 1 there, where it just starts by guessing with the 1 there. So I want to see, first of all, I think just for fun, I want to see the log a little bit of what it did. So CDCL, it's marking this as a guess because let's look at the log here, the logging code. It marks something as a guess when there's no deduction clause. But I think that's a little bit wrong. This is more like if the CDCL guess number is greater than 0, then this works. But if it's equal to 0, then what we're actually looking at here is a CDCL fix, right? So that could look like that to make the log a little more correct. So there we go. There's our fix value. And then it's making all these deductions at guess tier 0, right? So this is no longer, guess tier 0 is special. It's the one spot where we're not making guesses. We're making assertions. This needs to be this way. This way we want it to be. And then it's deducing the way other things will have to be from that. So all of this becomes irrevocable. And then it goes to see if, given this, it's still possible to solve the problem, right? Now, from there, what does it do? Well, I'm curious to see if it has any conflicts along the way. How does it... value conflict on variable blah. Is this under the learn, analyze the conflict, okay, so let's look for backtrack. Okay, so it does do some backtracks. 1, 2, 3, looks like it had to do 3 backtracks in order to solve the board with 1, 1 in it. Still pretty good. We can see it learned these gnarly clauses here. With Sudoku, it always seems to learn really gnarly clauses because it tends to put together 1 or 2 of these like 9-term clauses, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. There's all these 9-term clauses for things like the cell rule or the row rule or the column rule or the box rule. And then it ends up putting those together somehow and ends up with a big gnarly learned clause. And here you can see it's learned something very similar to this, but I'm gonna guess it's probably different somewhere. Yeah, right there you can see that it learned something almost identical to what it learned before, but with one change right here. And in both cases, that thing is the thing that it immediately was able to utilize as its next deduction after what it learned. And then in the last backtrack, it's somewhere else on the board completely. Okay, so that's cool. But that's still just one constraint. And so if it was going to start slowing down, it would start slowing down when we put in a heavier number of constraints. So let's look at now, before I do the next step, I'm going to put in a little helper here, Sudoku fix, and I'm just going to say, here's the FATSAT confix vars, here's my fix, here's my rank, and then I want to say U32X, U32Y, U32N, or let's call it num, and then we take the rank squared to make n squared, and we do fix val. Oh yeah, we need to give it the arena. So we give it an arena of fix n2 times x plus n2 times y plus num equals true, right? So this here, says, okay, you give me a number between 0 and 8, and that is the index for which number we're trying to set. Give me a value for x and y, which are also between 0 and 8. And all of those should, rank will be 9 when these are between 0 and 8. And then all of that should pick out the right cell. And then we set that cell to or the right variable. And then we set that variable to true. And then the rest of it can be figured out by deduction. So this can get replaced now with Sudoku fix scratch arena fix rank Sudoku rank n cell 8, or so, on the x position 8, on the y position 0, on the num value we set that to 0, and that should give us the same thing. There it is. Hey Batman, welcome back. How are you doing? Now what I want to do is look up a Easy Sudoku board. Actually, looks like I have a hard Sudoku board, because hard Sudoku boards have fewer numbers in them. Okay. So here we go. Here's my hard Sudoku board. First result on Google, I think. And I'm going to take 4Coder out of full screen for a moment. Go to a single panel. That way I can side by side it with this. And let's try to fill this in. So 0, 1, 2. Number 2 is 0, 1, 1. Oh, this is annoying. Let me actually do something a little different here. We are going to assert that 1 is less than or equal to x, and x is less than or equal to rank. We're going to do that for y, and we're going to do that for num. And then I'm going to subtract 1 from each of them for the purposes of actually, even simpler. We'll subtract 1 right away and then assert that they're all underneath the rank. And that way, when I do Sudoku fix, I can write it like this. x3, y1, num2, x4, y1, num7, x5, row y1, num8, x9, row 1, num3. So there's row 1. Row 2, position 6, value 9, 2, 7, 8, 2, 9, 1. JVS Tech asks, is this technically game development? No, this is definitely not game development. This is just software. Okay, gotcha. I suppose it is. Well, here's the thing. If I was building a Sudoku game, that would be one thing. But I'm building. This would be more akin to like building a task. I'm building a Sudoku task tool. Batman asked, have you disabled your subscriptions? Or is there some sort of region restriction? No, I don't have subscriptions. I think I probably qualify for them at this point. I got notified that I'm like qualified for affiliate status, but I'm not going to enable Twitch subscriptions. I'm not looking to raise cash on Twitch. If you are interested in following me to get notifications, that's an option. And sooner or later, I'm going to be announcing a way in which you can give me money in exchange for something, but it's not going to be Twitch. So if you wanted to support the stuff I'm doing, it'll be an option soon enough. But yeah, for now, no, there's no subscription or anything. All right. Oh, if you want it, gotcha. Yeah, I don't have any way to take your Twitch Prime money. That's a fair point. I can't take advantage of that particular free money that some people have to offer with what I'm doing. But that's okay. There are plenty of other good Twitch channels you could use that on. All right. 9, 4, 1, 3, 4, 5, 6, 4, 8. Oops. 5. 5 is the centerpiece. All right, square number 5 gets, what is this? That is 6, 4. This is 6, 7, 6 gets a 4, and 9, 6 gets an 8. All right. You know, maybe a better way to specify these moving into the future would be to go like this, right? 00278 0003 new line. I wouldn't even need new lines, right? You could just keep going and be like, let's see, how do I want to do this so that it doesn't x equals blah, right? You go like, here is my Sudoku board, 000 009 8 001 or 01, right? This would be better. Save that idea. Space row 7, 6, 2, 4, 4, 9, 7, and then on row 8, position 1, a 3, a 9, position 4 and 8. And on row 9, position 1, position 5, a 3, position 6, a 1, and position 7, a 6. Okay. So, let me double check here. Position 3, position 4, position 5, position 9, position 6, position 7, position 9, position 1, position 6, position 8. Yep, that makes sense. Position 1, position 3, position 6, position 5 for the 7 here. Position 4 for the 5, that's position 7 for the 4, position 9 for the 8, that adds up. Position 2 is 6, position 4 is 4, is that right? Yep. Position 9 is 7, position 1 is 3, position 3 is 9, position 4 is 8, position 1 is 8, position 5 is 3, position 6 is 1, position 7 is 6. Okay. So JVS Tech, I would recommend, if you know Abner Coimbre. He works on he doesn't stream, he hasn't streamed in a week or two, but he works on like a graphical terminal, and he takes Twitch subscriptions as part of funding his work. Last time he did a terminal click stream was in the last couple of weeks, or was like a couple weeks ago. He's been very busy because so Abner does conferences, and he opened up ticket sales in the last couple of weeks. So he's been focused on that. That's his main work. But on the side, he also does some streaming, and you can fund him that way. Cool. And I also am planning to do a collaboration stream over on Abner's channel sooner or later, so I'll be on his stream at some point, and you'll be able to be a subscriber in his channel while him and I are chatting on his stream if you do support him. So that's a good option. Okay. There we go. we've built our board. If we are going to build any more boards, we'll do it this way. But we've got a board. Let's see if it can be solved. Ooh, seg fault. Okay. Let's try... Let's try and understand why we got a seg fault. Remedy. Let's open up the... We gotta go to a different section here. FATSAT. Run. What did we hit? X is less than rank. Rank is... Oh, right. Okay. Rank is the wrong thing to test. It's not that it should be less than rank. It should be less than the squared rank. Okay, boom. Okay, so that's still pretty much instant. And let's see here. So if I take that, I'm going to move that into Notepad so I don't have to go back to full screen mode. 192784563 537 629 841 486 153 972 915 348 726 648 972 7235 16498 2614 95387 3598 67214 874 231 659. Amazing. So that's it. That solved this Sudoku for us, like instantaneously, which is fun. Very cool. Well, let's keep you up and do this. So let's see. I'm gonna do this thing real quick. So for this, we're going to do these two and a char pointer. We'll also want the rank. No, we don't really need that. So we're going to loop over y values. JVS Tech, this is my solving engine. I wrote it in the last stream. You can see, like, I mean, not 100% of it, but the core solver. I wrote last time, and a few things in there, like few of the helpers and stuff, have happened off stream, and a few of the helpers have happened in other streams, but the core solver, we did it all in one stream last time. It was not that bad. There's a lot of optimization we could do, but yeah, it's my own solver. It's very doable. I'm going to come out with a video about it sooner or later, about how you write a CDCL solver and then the steps you can take to optimize it. But it's actually not crazy. Very doable. Okay. So the read pointer is going to walk over the board, and it's going to go like this. We're going to go num equals rputter. If num is greater, rputter. And then we're going to subtract out a 0. If num is if 0 is less than num and num is less than or equal to 9, there, we'll do it. If we're in this range here and we got a valid cell, we will do Sudoku fix arena fix rank x y num, right? And then we want to Piggy Bank Studios, are you going to handle invalid chars before 0? I think I have. So our putter is an unsigned. So if anything is less than the 0 ASCII, it will roll over and be larger than 9, right? So everything is handled here, I think. I mean, I am assuming that my understanding of unsigned rollover is accurate. And I know C has funny rules about like, oh, it doesn't technically actually guarantee that rollover happens. But I think the rule is, well, yeah, the ones that nothing will roll over to 1 through 9. Nothing will roll over to 1 through 9. What? The only thing so when you have a byte, right? You have an unsigned byte, and you add or subtract something, it shifts the whole set. So each possible landing value corresponds to one possible starting value. So the only thing that can hit 1 through 9 are the ASCII values 1 through 9. Right? Everything else will roll over to something. Everything less than 0 will roll over to something bigger than the range 1 to 9. You don't like that I'm including C files? Yeah, I understand it's a different style. That's the Unity build style. So I understand it is an unusual style. The common way is to target each C file as a compilation unit and link them. But I like to minimize the amount of work the linker has to do to stitch together each target. So I only separate out compilation units when I'm actually building with separate parameters. Right, like if I'm optimizing one function and running everything else in debug, then separate compilation units, and we'll let the linker do it. If I'm building one thing as C++ and the other thing as C, separate compilation units. But these are all building with the same, like all of this is just code. So no need for the linker to be involved. Just Unity build those. Yeah, the linker's in a bad spot where it doesn't have the option to optimize or to go fast when it is also doing something rather trivial, and so just avoiding it is, I think, the right thing to do a lot of the time. So let's put that there. I lost the Sudoku board. Let's bring that back. I'm going to try transcribing the Sudoku board this way. 0003, 0000009, 801, 400, 003, 070, 905, 008, 000, 000, 070, 000, 500, 408, 060, 400, 007, 309, 800, 000, 800, 0316. Oops, I forgot a new line. 800, 031 600. So there we go. That is a much faster way to transcribe a board. And then we'll just go like this. Boom, 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 ba 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 ba. So there's our board. And then Sudoku fix board, scratch arena, fix. Yeah. So like JVS Tech, the single header libraries is like in the vein of the STB libraries where you have a header and then you can include that header with the impl define and that brings in the definitions. That's definitely sort of an inspiration for what I am doing here. Except, yeah, I really like to have, like, if I'm sitting here working, I like to have structs and function prototypes on one side and definitions on the other. And if they're both in the same file, then annoying stuff happens, right? If I'm working on this file and I've got, let's say I'm working on my struct right here and I'm working on my functions right here, but say this is a function definition. I'm like implementing this and looking at this and I go, oh, let me make some adjustments. And then I do, like, you see how it starts infecting the indentation across the file. So it's just, I like to have the file split, but it is sort of more like a single header library mindset, but with a couple of file splits just so that I can side by side things and stuff like that a little easier. But I try to keep the number of split files minimal so that it's clear they are sort of linked together in the way that a single file header library kind of thing is linked together. All right, so let's see if we can specify boards that way moving forward. Here is the board, F1. Oh, right, you still need the Sudoku rank. Boom. Okay, something went wrong. Let's take a look in Remedy here. Y is humongous. How did Y get to be humongous? Y started off, oh, they're starting off at 0. That's a mistake. Okay, so when we do fix board, these should start at 1 and they should have an inclusive range. Boom. There we go. And there's our solve again. So that's very cool, and we can say here, no need to manually specify all of the coordinates anymore. We'll just use a handwritten board and then parse it. Very, very straightforward. Okay, so let's see. That was not a very long time and felt very productive because we can now say that just seems to have worked. Like fixing variables, not a problem. You plug it in and it starts working apparently. Very nice. So let's work on the second part here, higher level constraint writing API. So what do I mean by that exactly? Well, what I want to do is look at my Sudoku rules and point out some patterns here. So after doing a little bit of reading other Sudoku APIs and stuff, I've already got some hints about, or not Sudoku, SAT APIs. After looking at some SAT APIs for constructing these formulas, I've already got some hints in mind for what I could change, but some stuff here that is an ongoing pain. So there's always this issue of coming up with the way to index your variable. So you end up with the situation where you have a structure you're trying to specify. And in the case of Sudoku, it's very regular. It's like a 9x9 board with 9 possibilities in each cell. So it's like the number of Booleans we end up with is 9x9x9. That's the number of Boolean variables we're working with here. And so indexing that is sort of one of these things of like, okay, if I know my X and my Y and my num, it's just going into a grid and getting that. That can get more difficult, and how to deal with that is something I'm not quite sure about. I think we would need to wait until I had a problem other than Sudoku that had that more complex structure to really get into it. But what I kind of think you end up with is things where you allocate indexes, right? So you say like, okay, give me 9 indexes, and then it returns the first one. So you would have like, you could imagine, right? You have your board, and it's going to be like a 9x9 board, and you're going over everything in the board, and you're saying, okay, board X, Y equals FATSAT con alloc vars, and here's your builder, and here's how many vars you want. So you get 9 variables, and then this puts an integer there. That's the first variable, and then there are 9 of them in the run, right? So it like is incrementing a counter, and then you have like a variable here that you're holding on to that's like the name of some object, which each object is just a collection of the variables that are associated with that sort of conceptual object. So that's one thing we could work on. But I don't want to do that because, like I said, we don't have a very good use case for that yet. Like, this is not a use case where it's really necessary or even convenient to do it that way. It's perfectly fine to just index into the grid directly. But some of these other things, right? So we have loops over variables where we are sending them all to, we're ORing them all together. And loops over variables where we're doing pairwise knots. And I wonder if, like, so something I have seen is this idea of like one hot. So the idea of one hot being you're putting in a collection of variables and saying one and only one of this set of variables should be true, right? Now the question is, how do you specify the set of variables? If the answer is you have to do something like setting all the strides. So you go like, okay, it's one hot, scratch arena, here's the builder, and then cell index is the starting point, and the stride is 1, right? And then the number of variables is 9. Then that works here. Does that work in a bunch of cases? I don't know. Like, if it starts to be super heterogeneous, like in the case where you're allocating out different object space sizes and stuff, you start wanting to be able to specify a list of variables. So it could be that you just want to go like, hey, let me make a local vars list that's like this, right? And then it's like cell index plus 1. We just specify this out, right? You could do this as a loop. I plus equals 1. Cell index plus I, and then you're going like this, right? So now you just give it a list. And then the annoying thing is you have to build lists on your own, and then you give it a list and it does all of this for you. That is cool. It's very generic. Like I said, the annoying part is it doesn't automate the arrangement of the variables for you in any way, but maybe that is the best starting point, because we can then say like, well, in some cases you can do it by striding or something. Piggy Bank Studios, I could give you a description of the constraints I have in Princess Castle Quest movement system and see if your solver would solve it. That would be fun. I have a couple of other game ideas in terms of games I know of that I want to put into the solver. And I don't know, Sudoku or Sokoban might be quite hard, because I think Sokoban is just a rich state space, which is difficult. Even if it's trivial to sort of back solve certain paths, SAT by itself, when there is, you know, a rich state space, doesn't see the hidden logic if the state space is rich enough, right? But it probably can solve it. I want to solve, do you know the puzzle where you have a bag of corn and a chicken and a hound, and you have to cross the river, but you can only move one of the objects at a time? I want to make a solver for that, and then make a solver for the like Pico 8 super version, Pico 8 river crossing. Have you guys ever seen this game? Yeah, have you ever seen this game right here? Here, let me... Let me know if it's too loud. Because I've not calibrated my desktop. Oh. Pretty loud for me, but I got it adjusted to a good spot for me. Okay, so this game here, let's just see if I can play it. Reset cartridge. Continue. Cool. Here we go. Okay. So my moves are arrows to move my characters, down to grab an item, Z to fire with the gun, X to undo the last move. So here I am this dude. And in this game, you are playing the river crossing game. So I can take my goat. Well, let's see if I cross the river. What happens? Oh, the goat ate my cabbage. The hound ate my goat. The hunter shot. Wait, what? The hunter shot my. The hunter shot my wolf. Oh, it's a wolf, not a hound. Okay. All right. Too much. So let's say. Wow. Okay. So if I leave the cabbage with the goat, that's a problem. But if I do this, the hunter is still gonna shoot the wolf, right? What do we got here? The monkey took the cabbage and the hunter shot the wolf. That's no good. All right. Well. And, you know, you keep going with this. You're like, okay, you can't pick up the washing machine by yourself. So the hunter has to be there for you to pick up the washing machine. You know, it's got all these rules. I would love to write down these rules as a Sudoku or a SAT solver case, because this puzzle is neat and it's so heterogeneous. They're so different. Like the goat and cabbage and wolf act like the original puzzle. And then you got the washing machine. You can pick up the gun and I can shoot it, so I can shoot things. What is that going to be for? Well, I don't know, but you can encode the rule and find out. And the goal is to get all of these things to the other side of the river. I think we can make a SAT solver tell us the answer. That's a fun game, by the way. So, whoops, don't want to hide that. Let me put this back into this mode. The, getting back to, what's going on in chat here. So, would the solver be able to tackle something like pathfinding? So, it could do pathfinding. Again, I don't think it would be good at it. I think it would struggle to be efficient at it. And it is not good at, like, optimal solution stuff. It's not very good at... SAT doesn't do optimization problems. It does constraint problems in the sense that it tells you whether or not the constraints... how to meet certain constraints. But constraints aren't the same thing as optimization problems, right? An optimization problem is one where your score gets better as you arrange the pieces, whereas constraint problems are ones where you either have valid or invalid states as you arrange the pieces. And SAT is in the constraint category completely. It is not good at all if you want to optimize something like a Pathfinder. So the way you would have to use SAT, you could use it as a piece of a Pathfinder to find an optimal path by doing this. You use SAT to generate a solution, right? If possible. It'll tell you if it's impossible, but if it can find a solution, you then eliminate one of the nodes that it's using. You say like, okay, what if you had to do this, but you couldn't do this, right? And then you guide it down and you get it to generate multiple paths and you compare them. So really, like the worst, and that's what you would do with it. Like, it's just not the right tool to get started. Now, what you could do is you could make like a SAT variant that is an optimization problem, and then you would use a different algorithm for solving it. And the way you might think about that is, instead of saying here are the Booleans that are either evaluating to true or false, you'd have certain Booleans that evaluate to certain scores or something like that. You could set it up so that clauses in your C and F each contain a weight, and you're trying to get as many of them as true as possible based on weight. Rather than getting all of them true. And then you've turned it into an optimization problem. But no, there is kind of a tricky divide between constraint solving, where you arrange pieces to get valid and invalid states, and optimization problems where you're always valid, but you're trying to arrange the pieces to get the most valid thing. And then, of course, there's stuff like the real tricky stuff where you're doing both at the same time. There are valid and invalid states, and within the valid states, there's optimization. You could definitely direct it towards preferring simpler states heuristically, but the question is, at what point are you just piping your heuristics through the wrong core algorithm, right? Like if the reason you want to use a SAT solver for your pathfinder is because your paths are themselves built out of logical circuits, like if your pathfinder is a pathfinder through a maze where you flip switches and doors open and close as you go, then maybe there's an argument that SAT would play an important role in that pathfinder, and that there's a reason to push your pathfinder through the SAT solver. Um, but just if you have a general graph of space with no dynamics that tie into Boolean logic, then I just don't think it's the right tool. It's like too circum. It's too much like going outside of the correct domain. Yeah, so Sokoban is a good example of a place where I'm not entirely skeptical of the utility of putting SAT in there somewhere, but so there's an idea of like a generalized solver, like an SMT solver, which might be another thing to think about here, which is in SAT we're just doing Boolean logic, but often what we want to do is have like arithmetic logic or other kinds of logic that are a little more rich than just Boolean. So variables can then range. Like in my Sudoku 6 case, I don't have integers, so I can't make a cell contain a 1 through 9. Instead, I have a Boolean for each state, right? But if I had an integer theory and integer constraints, then I could specify it in like 81 variables and a much smaller set of constraints. But a SAT solver doesn't know what to do with that, so you're getting more specialized solvers. And so then what people do is they stitch all these solvers together with SAT as kind of the beating heart of it. You go like, okay, these integer logic things, at some level underneath them, can be thought of as Boolean logic, right? So x is less than y is an integer logic thing, but it's either true or false, and so the true or falsiness of it can be a Boolean variable in the SAT solver, and maps to a constraint in the integer theory, right? And so you probably start, like, you're definitely seeing that SAT plays a role in other places, but there is a limit to what it is good for on its own, without additional specialized things. So like if you were going to use SAT with a Sokoban to solve Sokoban, you might combine it with a pathfinder, like a classic pathfinder, and figure out how to pull out the logic of blocks that cover certain squares or block certain paths, so that you can use the pathfinder to extract out the Boolean logics of where blocks go, and then the pathfinder's job is to take care of all the space or arrangement of space that the SAT solver would just grind to a halt on by itself. It's an interesting question, though. I've never looked at Sokoban solvers. My understanding is that that Sokoban is a special case of SAT. Like, it is possible to make. If I remember correctly, I think that if I give a computer a Sokoban instance and say solve this, it is just as hard as a SAT problem. So I do think there is something interesting about the question of how to write a Sokoban solver. That you're making me curious about going in that direction. Okay, so I was trying to figure out. Right, I was doing this one hot, and I was let's get back into this. I'm trying to simplify this. So this one hot thing would replace all of this and one of these, right? It would boil this all down to just one. No, Piggy Banks. You don't have to apologize. I'm having a great time. I'm trying to get back into it so we can make progress. But I am going where the conversation is going because it's fascinating stuff, and I'm much more interested in being excited about it than in I'm much more interested in being excited about it than anything else, and I'm excited about working around it. I'm also excited about talking about it. So let's see, the one hot would then over here, how would it look? So here we're building yeah, I is a fixed value now, and the cell index gets computed over and over again like this. So this is how we would end up generating the 9 variables for one hot. That doesn't seem that bad. Like, you can see I'm pulling out the core logic of how I index into the grid. So that can't be magically handled. That is Sudoku specific logic. And that makes sense that it would be. But the idea that once we know the set of variables that are interested in this that bear this relationship, that we would just pass that down, I think that's a good helper. So let's try going, okay, FATSAT con 1 hot takes in the arena, the builder, a list of variable indexes, and a count, right? And then the way we would build that, con not, okay, so then what we have to do is kind of like recreate this pattern here. So we need an at least 1, which goes over the count, grabbing the var indexes as it goes and ORing those together into the builder. That builds the at least 1 piece, and at most 1 goes like this. It goes over the count in a sort of triangle iteration. So this is an n squared iteration of the index, or the input. These come out like this. I's and j's come out together like that. And then we make a both, a not both, and then we combine that into the at most 1. And then finally we want to make a result. And the result is going to be the and of at least 1 and at most 1, right? Like that. And there's our result. So a 1 hot is constructed out of an array of variables. We loop over them once to form an at least 1 constraint, and we loop over them as a triangle to form an at most 1 constraint. And we stick those together to make the 1 hot constraint and return that. So why don't we, while we're at it, at least 1. You know, why don't we like just do this? At least 1. And then at most 1. At most 1 does this. At most. At least 1 arena builder var indexes count. At most 1, and add those together. Right, we don't want this on Scratch, we want this right on the arena. All right, so we got some high-level constraints there. Now let's see if we can use that to simplify these. So with each of these, what we want to do is, well, I guess I kind of want, why don't we do something like this? We're going to make a just an array of variables that we can reuse over and over again that looks like that. And then we'll have loops like this where we go vars I equals, in this case it's cell index plus I. And then we're doing FATSAT con 1. Why don't I call this exactly 1? FATSAT con exactly 1 on the Scratch Arena builder vars n2, right? And then there it is, 1. Did that work? Boom. If it worked, then, yeah, looks like we still have our solution coming out. That's a really good question. I've heard Picky Bank Studios asking, he's not asking me, they're having a chat in chat about how SAT and SMT solvers show up in optimizing compilers. And I've heard about this before, about how they get used to validate certain optimizations. And the question is, do the SMT solvers run during an optimization? Like if I run my compiler in optimizing mode, does it run during the optimization, or does it run offline to validate the optimization concept or pattern? Okay, and JVS Tech is saying that it tends to run as an analysis after optimization. So JVS Tech, can I ask, do you mean like when I run my compiler, if I were to run my compiler and it was the one you work on, it would run an SMT solver right then after the fact of running the optimizations. Like your compiler goes through an optimization mode, and then inside my process, it runs the SMT instance to ensure that the optimizations it came up with were actually valid, as like a double check, a sanity check, safety mode thing. Is that the idea? You can see this is just like massively reducing the amount of code I have to write to specify the Sudoku constraints, so that's cool. Okay, gotcha. So a JVS Tech is saying that generally the it's a tool that you would run after the compiler. That is not a part of the main invocation of the compiler. That's a separate sort of testing mode. Makes sense, makes sense. All right, so in this case, we loop over the y values. And so whichever y we're looking at, how, yeah, we want to grab this and do that plus I. Really with all of these, this is what we're doing. It's just in some of them I'm like complicating it with an optimization by pulling out a constant first. But let's not do that. Let's actually simplify the syntax of the constraints so they all can just look like that, right? So now the only difference is whichever loop we're going over last is the one that we use to generate the list of variables for the exactly one call. Exactly one. And then we visit each box. Now boxes are a little trickier. But not too tricky. So yeah, I'm going to use the same terminology I did here, K. And now the question is, yeah, calculate X and Y from K and box X, box Y. So this tells me which box I'm in. And the K tells me which cell in the box I'm in. And then I plug those in to here and I say, okay, give me exactly one of those. All right, and there we go. Okay. It's really cool seeing how much it actually deduces at guess 0. Let's take a look. Now that we've put in a full... Whoa, look at that. This problem is constrained enough that it doesn't actually have to make any guesses to find the solution at all. It just deduces its way to the solution from the start. I mean, I guess that kind of makes sense. I'm just surprised. I would have thought that the... Let's look at the board real quick. If this is a hard Sudoku, then I would have thought that like there should be places where what's the first deduction the system makes? It deduces, so it's making a bunch of false deductions. False deductions aren't interesting because these are just the variables that get set to false are just the ones that correspond to putting two numbers in the same cell, right? If I've already fixed a particular cell to have a certain number, oh yeah, Piggy Bank Studio, that's a good question. I should check that. But what I was saying is, so where does it deduce a true? Because that's where it's actually deducing the placement of a new number. And I want to see that happen. Okay, so right here, its first deduction And as usual, I don't actually know where 618 happens. Let's do a little bit of calculator work. So divide that by 9 to find out. Okay, so this is the 68th block or cell. So 68th cell happens in which row? The 7th row. Or row index 7. So if I put, let me just double check some thinking here. If I went to row number 7, I would be at 567. If I then do 618 minus, oh, I don't have memory. What's the deal with the calculator? 618 minus 7 times 81, 51. Okay. So dividing that by 9, we're talking about row 7, 5. Okay, so that's actually row number 8, 6, because these are 0 indexed in this particular situation. Okay, so 7, 5, 618 minus 7 times 81 plus 5 times 9. Okay, again, 618 minus 7 times 81 plus 5 times 9. No. Okay, here we go again. 618 minus 7 times 81 plus 5 times 9. 6. Okay, so it's position 7. Got it. So that is this cell, let's see, 7, 0, 1, 2, 3, 4, 5, 6, 7, 5, 0, 1, 2, 3, 4, 5, 7. Okay, so it's placing a 7 there. That's its first deduction. That's this 7 here that it's deducing. Yeah, so you can see that that's actually like immediately. So this board might not be as hard as I thought. It might not be a hard board, or it might not be hard in the way I wanted. So what I mean when I say a hard board is I would like one where, yeah, you can even see right here, this 7 is deducible too. I would like one where some deductions cannot be made without using hypothetical logic. It looks like this one might be one that you can solve just by noticing cells that only have one possible value. So simple deductions are like, hey, this cell can only be one possible value, plug that in, propagate. A hard board would be one where you get to a point where the only way to see progress is to go, oh, whatever I put here, it would still not be able to be this because that, and then you have these little more high order logic. And I think that would require, since the SAT solver cannot, it does not perform like pattern analysis like that. It instead makes progress by guessing. So the fact that this doesn't guess suggests to me this was not actually a hard board. So maybe I'll go track down an actually proper hard board. But before I do that, Piggy Bank Studios did point out something. I haven't done anything to verify that this is working correctly. Like, I kind of am just taking for granted that this is the solution. I don't have the true solution here, but what I could do is run I could do my own Sudoku verification, right? That would be probably the easier way to ensure that it's doing the right thing. Verification. So the way this would work. SF says that it looks like it matched. Okay, I will save this for later then. If it looks like it's working, that's what I want to know. Very good. All right, I'm still going to do this at some point, but not necessarily right now. So we we did some high level stuff. We did these. Now the trick is, if there are any other good high level ideas, I won't know them until I put in a new problem, because like I just don't have a test case interesting enough to push me to find other useful ways of arranging patterns in a SAT formula. So I might need to build a new problem, like the crossing the river problem. We might do that next. But before I do that, I do want to try to actually find a properly hard Sudoku board and see what happens. So let's see. Let's grab this hard Sudoku. Let me pull up my notepad here. Notepad instance, and here is the Sudoku instance 000063000 902 000 007 004 000 090 050 003 008 000 000 700 000 169 501 000 040 000 800 200 020 540 600. All right, let's see if that is hard. Yeah, JVS, I doubt ChatGPT would be the helpful one here. I kind of can imagine the conversation I would have with ChatGPT about this. I'd be like, hey, can you generate a Sudoku board for me that is valid but very hard? And they'd be like, sure, here's a Sudoku board for you that is valid but very hard. And it spit out a bunch of numbers. And I'd be like, hey, I just plugged this into a SAT solver and it turns out it's unsolvable. And it would be like, oh, sorry, my bad. Let me change that. And then it would print back the same Sudoku board again. Like that's the conversation loop I anticipate. It's still instantaneous. Okay, but it does make guesses. That is cool. And it has to backtrack, which means it made... Oh, look, it did so much backtracking. Wow. It was still so fast. It was still so fast, but it did have to work a lot harder. So it only had that many fixed things at the beginning. Was it able to deduce any true values at the beginning? Or did it have to... here's all the falses that it deduced. But did it deduce... Okay, so it did get one true deduction here, and here, and here. So these are the things it could fill in from that board using direct, simple logic. And then it had to start guessing. And then it came up with this. I think now what we should do is write a... let me grab this. Scratch. So here was our original board. Here's our solution board. And yeah, I can see that these did get respected still, so that's good. 5, 1, 6, 3. Yeah, it's looking good. It's looking good. But let's I don't actually have any profiling plugged in right now at PiggyBank Studio. When I say it's fast, what I mean is I did not manually feel it. I did not, like, a Sudoku, a SAT solver. SAT is an NP hard problem, so at the limit, pushed to its limit, we would expect that some problems that we put into it should feel like they take a minute. Like, we should feel them at human time scale. And the fact that we're not feeling that means that, one, my SAT solver isn't being pushed very hard, There's no way my set solver is fast. I haven't optimized it. There's no question that it's slow. But it's surprising to me how many things it can actually make progress on when you just use the CDCL algorithm in the dumbest possible way. It still just like eats it up. It's not like it takes a minute, which is cool. And it's very encouraging because look at how many variables there are. There's like 700 variables in this problem. It's not the biggest problem ever, but a 700 variable formula, that's rich enough that I could imagine doing some cool work with this. Like if I had some procedural generator and I wanted to like have it be a thing where I could plug in some constraints and see it then like fix some things that I want and see it fill in the rest of my game's procedural generation from there. It's like, this could do that. This seems like it's within the range of doing interesting stuff for me already. It's cool. So let's do a quick Sudoku board verifier now. Sudoku verification. All right, for this we need a board array. We'll put that on Scratch. N2 times N2. We're gonna need, yes, and of course only if we actually were able to satisfy it. If I give it an impossible board, so one thing is it might be slower when it's impossible, right? Because when it's solvable, it kind of just deduces its way forward. It might make some wrong guesses along the way, but you know, if there's a solution, then it just keeps making forward progress. Whereas if it's unsolvable, then it might have to iterate the entire space through really ridiculous detail just to come to the conclusion there's no solution. So maybe the reason it's fast is because I'm putting in solvable instances. The tricky thing is if I start with a board and make a change, it's not guaranteed to make an unsolvable instance. It could, like I could remove a constraint and add in a different one and just as easily end up with an even easier board that has multiple solutions, right? Making an invalid board would be something I'd have to craft manually. But that's fine. Yeah, SF Gardner, it should detect that. I haven't done that yet, but that's a good idea. We'll put in some directly invalid boards. I can engineer some exactly invalid boards and some boards that will be very trivial to find their impossibility. So we could do that at least and make sure that it's catching on-sat cases correctly. That should be doable. Let me do this bit first though. So we're gonna iterate the board. We calculate the numbers, and instead of printing them here, what we're doing is we're doing this. So why don't we do this actually? Sudoku board from solution. All right, so if we have a solution, we'll fill out a board. Then we won't have to do this anymore. We'll just do print out board column plus row times N2. Right, so this will just use the board again. This will use the board. And then we can do a Sudoku verify right here. So this is going to be validate Sudoku board. And so again, if, well, let's change the ifs now. If the board is not 0, then we have a board and it should be valid. Let's ensure that it is. Awesome, thank you. I'm still going to write the validator this time just so we can get that answer automatically without me having to wait for chat to find out for me. shouldn't be too hard. All we have to do is check the rules. So all the board already has a number in each spot, right? Well, let's ensure that. So let's grab the N2 again. And in this case, I actually am going to use an N4. That N4 is the size of the whole board. And we're going to ensure that, let's see, we'll do it in waves. If board I, if it is not the case that 1 is less than or equal to board I and board I is less than or equal to N2, then valid equals 0, break. And then let's see, we want to check each row. Then we can scan, let's see, for this, the easy way to do it would be I think what we want is like a little scratch pad here filled with booleans, and we'll do mem0 the scene and 2. So for each row and column, if we get the num from board row plus column, or column plus row times n2. If we've seen this number before, then valid equals 0, break. Otherwise, we mark it as seen. We do that on every row, right? So that validates the rows. Then we want to switch these around. That should validate the columns. Yeah, they should all sum to 45. I don't know if that proves that that does check. That is so Flexon is suggesting that I sum each row and check that they are all correct. Sum each column, check they're correct, and sum each square or box and check that they're correct. And while that is a check that is true of a true board, I don't know that that's a necessary condition. I don't know, is that a sufficient condition? I don't know if it would be. It's a good idea if I wanted an easy check, but I don't know that it's foolproof. It might be, but I don't know. Okay, replace this with K now. And what we're going to do is we're going to get U32 box X equals yeah, that's kind of what I'm thinking. It wouldn't catch cases where there are duplicates that happen to still work out, but it'd have to be a pretty unusual failure. Like it's definitely true that your suggestion would catch accidental incorrectness. It would only be vulnerable to malicious incorrectness, right? You'd have to very carefully engineer a board that would not be a valid Sudoku board, but would in fact pass your test. Yeah. It'd be its own problem for sure. Welcome, by the way. Okay, so then road becomes KK, and so we get X is equal to box X plus KK modulo and divided by N. YX gives us a number. All right, if I did that correctly, then we should get to the end here, and if it is not valid for any reason, then we can fprintf standard out board invalid board. Let's see if that works. So I don't see invalid board, which is good news. Let me give it an invalid board real quick, just to be sure. So in order to make one of my boards invalid, what I'm going to do is, after I've built it, I'm going to swap board position 0 and board position 17. That should break it. Boom. Run. Unless I got unlucky. Yeah, okay, so invalid board. Yeah, there was a 1 in 9 chance that I would have swapped two things that had the same number in them. But that did not happen, thankfully, and so there we go. I think that the validator is probably working. Cool. Yeah, I do a lot of math stuff for sure, but I try to bring it to the real world, make it worthwhile and accessible as much as I can. But I'm a math head. I can admit that. I know I make I make it a common topic for sure. Okay, so we've got a board validator, and now I want to look at Asaf's suggestion that we do some invalid boards. So first, let's replace each of these with just zeros. Okay. So there's an empty board. Now, what if I put in a 1 here and here? It should just be impossible, right? And there it is, right? It finds the conflict and says, no, you can't. So anytime you put in a direct conflict, anytime you put in a direct conflict, it's going to what's what I'm looking for? It's going to directly notice that in the process of deduction. So it's not like it did anything super interesting here. Rather, in the process of deductions, it just got to the point where it saw one of its constraints was never going to be meetable. And that makes sense. But what happens if I push, so there we go. I arrange so that 9 has to go here. And then I arrange that 9 will also have to go here, but both of them are indirect, right? So 9 wants to go here and here, and the only way that's a conflict is through this column. I still think it's going to figure it out right away. And that's because it's going to be able to deduce those, right? Like it's going to be real hard to get it to fail late. Oh, 8 has a conflict here. 7 and 8 are in conflict. You're right. Switch these around. Good catch. Still, it finds that it doesn't work. So in this case, by the way, I'm saying valid as in solvable, not like a valid Sudoku board as in a um, fair game is one which has only one solution. It has exactly one solution. And we're not doing anything here to validate that my boards have exactly one solution. We're only validating that they have at least one solution, right? To prove they have exactly one solution, what you'd have to do is add in another constraint. Actually, that's something we could do. We could make a thing that says, hey, here's a Sudoku formula. Here is a solution, like here's a set of constraints, and here's a solution. I want you to find a solution other than this one. And if it can find one, then your board is not a valid game because you have two possible solutions. And that would be a useful tool to have if we're going to use this for crafting Sudoku boards, is the ability to say, yes, there is an existing solution and it is a unique solution. So maybe that would be a fun way to push the solver a little bit. See what would it be like to write a thing that prevents me from having duplicate solutions. JVSec, that is a really cool idea. So JVSec is suggesting using bit shifts and then summing up the right. So instead of doing scene, which I did, you would have like, you're suggesting something like this. So first we make sure that everything's in the legal range, 1 to 9, and then you go, here's my accumulator. And I do accumulator or equals 1 bit shifted by the num. And then when it's done, you would do if accumulator does not equal the valid mask or something, right? Then you're invalid. Yeah, Piggy Bank Studio, that's what I was saying. I would like to go build that. That seems like a useful utility to add. Like, if this is a library, let's give it the kinds of tools you'd actually want. So, say I've got a formula. Let's put in a board again. So this is invalid. Let me replace it real quick. 1, 2, 3, 1, 2, 3. Do I want a Sudoku board, or let's get a, I've got one right here. Let's grab this Sudoku board that we were using a minute ago. And let's say that we got in here and we dropped a constraint, okay? Now, hopefully this board is set up so that its constraints are necessary. Right, and the constraint I dropped hopefully will be enough to make it solve. So by removing a constraint, by unconstraining it, I'm not making it harder to solve. Like, I'm actually making it less constrained. There might be more solutions, and we want to try to see if that occurred. That's the next goal. That's a fun goal. So let's pop in here. Higher level constraint writing APIs. We've got exactly one variable true. We did that. Let's do not non-duplicate solution. Find non-duplicate solution. Okay. Okay, so the way that we would do this is, let's go through the flow of how this works. So we build our constraints. Those aren't going to change. We're going to use the same problem. We build our fixed variables. those are going to stay the same because we're solving the same problem. So we want to solve the same problem twice, but we want to enhance the problem on the second pass. So that enhancement is going to be that we take a solution, which is an assignment of the variables that we got from a previous solution run of the solver, and add in a new set of constraints that say that it is not exactly that. So how would that work? Let me think. It would have, say I've got 100 variables and I have an assignment for all of them. Then all I'm doing is saying one new clause. It's actually one new clause which says one of these variables has to be different, right? So if I have, think about this. If I have x1 is true, and x2 is false, and x3 is false, and x4 is true, and so on for 100 variables, right? Then all I would have to do is say, take whatever formula we had before and add in the rule that we want x1 to be false, or x2 to be true, or x3 to be true, or x4 to be false, and so on, right? It would make one big giant clause like that, where we're just saying, hey, one of these, we want it to be different. Any one of them can be different, and that's good enough, but we want something to be different. Okay? So, we can actually do that right on top of the CNF formula, because if this is a CNF formula here, then adding that makes it another CNF formula. So all we would have to do is say, take the formula we had. Now, we have a problem, which is that the solver modifies the formula when we run the solver. Like, it sort of consumes it. This here, right? It does it's consuming this formula. We could say we just don't like that as a behavior and maybe make a copy. But before we go and build that into the solver itself, let's just say, either way, we're going to need a formula copy function. So let's build that. Converting, so that's how we get the formula. Yeah, so let's write right here, CNF formula, FATSAT CNF formula copy, arena, and then you give it another formula here, right? Formula. And let's write that. So this way we have some kind of utility sitting around that lets us copy this data structure. And what is this data structure? That's what we're going to want to have in view over here. So the way we copy this is we create a new blank one. We loop over the clauses of the existing formula. Formula first, we look at each clause, and we do look at that. I already have a way to copy a clause. So FATSAT CNF clause and new clause, or clause copy equals FATSAT CNF formula CNF clause copy, arena clause. So that makes a new copy of the clause that we are looking at. And then we just have to chain that into the new formula like this. Result first, last, clause copy. And finally, we can get the formula's clause count and variable count out like that. Okay, so that should give me a way to copy a formula. So for now, I won't bake the copy into the CDCL solver just yet. I'll just do a formula. Well, I really don't love destructive operations if it starts pushing me to have to work around them all the time. So why don't we do this? We set up a Scratch arena right away. Yeah, let's just go ahead and copy the formula right up front. It may be slowing things down, but the slow part of a SAT solver should be much slower than this. For a while. So if this comes to the point where it's really egregiously annoying to have this baked in, then we can undo this and we can make a low-level version that lets you go as fast as possible. But I just like the formula data structure itself is probably gonna change before this matters. So yeah, we'll just make a copy like that. Now you don't have to worry about your formula getting destroyed when you pass it to CDCL. Your formula stays intact and the solver operates on a copy of the formula locally. Now that does raise a question. When it learns new clauses, put the new stuff you learn on Scratch. Oh, that's why I don't put it on Scratch, because yep. Okay, so what's happening with Arena here? It might be helpful to pull this out into a separate function. Flexin? Yeah, sorry, I'm kind of doing some deep stuff here. I am just making sure that when I'm just making sure that when I pass a formula into this function, it doesn't modify the formula in place. And then I am adjusting the rest of the code around that change. So it looks like here, I have a spot where I should pull it out into a separate function just to make it a little easier to reason about the relationship of the Scratch and permanent allocations. Because I don't like to get into a situation where I have scratches within functions. Like I have a function with an arena and a Scratch arena. If I get to a point where I want another Scratch relative to that Scratch, then that's where I go, well, that needs to be another function. Zarbaz47, are you interested in what we're doing today? What's going on? Sarbaz, are you familiar with what a SAT solver is? To answer your question, Flexin, a formula is gonna, well, you're gonna find out what a formula is as I explain SAT solving. So for both of you, we're working on a SAT solver. I'm gonna kind of get a temperature for how much y'all know about SAT solving and CNF, and I'll explain some of it for you. But I gotta kind of start by figuring out what is and isn't new information. Okay, so when it goes into learn mode, I'm gonna have it do function. What comes out of learn is, I'm not quite sure yet. FATSAT CDCL learn, but it's going to be something like this. something like this, but maybe not all of it. We'll figure it out. It's definitely going to want an arena temp, scratch, arena, get scratch. I'll update, I'll take a look back at the chat in just a second. I haven't forgotten y'all. I'm just making enough progress on this that I won't forget what I was thinking. Cool. Okay. So what do we got? Okay. So we'll start with the easy one. JVS Tech, yes. Function is a define. It's a little bit, right, it is a sort of syntax sugar over my underlying system of like being able to control which things are linked statically or within object files, which things are linked across object files. So function basically goes on anything that's going to be linked just as a locally, and then if I need it to link across object files, it's a linked function, and if I need it to link across like binaries, so DLLs or shared objects, then it's a dynamic function. Now, for the people who want to learn about SAT, are you familiar with Boolean variables and logical operations like and, or, and not? Because the main idea of SAT is based on starting with a formula of Boolean variables and, or, and not combined together, right? So we put a bunch of Boolean variables together, we go ands and ors and nots to make some big formula out of them, right? Some big, we call it a formula, we could also call it an expression or a logic circuit or a logic gate. It's something like that, right? So we start with one of those, but we don't know any of the values for the variables. So when you learn how to write ifs in your programming, right, you learn how to do like if A or B, and you learn that what happens when these are true and false. These A and B already have values, and you evaluate to figure out, oh, if one of these is true, then we'll go. SAT is running the other way around. In SAT, these don't have values yet, right? So we're looking at a formula like this, but we don't know. They're free variables. We don't know what their values are. And the question is there some way to assign values of true and false to the Boolean variables so that the whole formula is true? Now, in basic cases like this, it's trivial. It's like, yeah, of course there is. But I can make cases where it's not possible, right? Like this would not be possible. And so that's a trivial case where it's not possible. And then you can use a solver that can look at these formulas and answer this question. Yes, it is possible. No, it is not possible. And you can take it a step further and say, yes, it is possible, and here's the way to do it, right? So that solver can go, yes, it is possible to solve this problem, and here's how you set each variable to make it possible, right? If it was impossible, it would just say, no, it's not possible. But if it is possible to make that whole expression true, the whole gate come to true, right? The whole formula evaluate out to true, then if that's possible, it can say, here's the way to set each variable so that you get the true result for the whole formula. And that's what the SAT solver does for us, right? So I'm working on I've already written the SAT solver in the previous streams, and it does this, right? You put in a formula and it does this. So when we say formula, we're talking about, well, it can be one of two different things, but we're talking about some kind of way to encode that constraint structure, the Boolean logic structure. And that's our formula. And the solver is trying to figure out, yeah, it's a multivariable equation in Boolean algebra. That's exactly right. Yes. Yes, you're getting the right idea. It's about figuring out the inputs that give you a desired output, and the desired output is very simple. You want a true signal. You want a positive bit, something like that, right? That's the desired output, and the question is, can it be done and how? And then what you can do is, like, we're doing Sudoku with it. So I put in some logical structure that encodes it's a Boolean formula that encodes the rules of Sudoku. And then I can fix certain variables in there and say, like, well, these ones need to be fixed in certain ways. And the solver can then say, yes, here's a solution. And so we are able to solve or Sudoku problems like that with this thing. Now, it's a hard problem in the sense that there's no polynomial time solution. The solver for it can take a very long time to solve certain instances, but in lots of common cases and small enough problems, modern techniques can actually go pretty fast, and that's why it's worthwhile to write them. Okay, so that's what a SAT solver is, that's what we're working on, and that's what a formula is. It's the sort of the input to the SAT solver. You could think of it in a couple ways. It's like a constraint solving system, or it's like an automatic puzzle solver, and you put in your puzzle and it tells you if there's a solution, but it takes its puzzles in the format of a Boolean formula. Yeah, so if you're interested in that part, we'll get back to it in more detail pretty soon. But like right here, I can build the constraints of Sudoku. And when I say constraints, what I mean is the formula. And so I build it, and you can see I'm going like, okay, for each cell, we're going to have 9 variables, because each of my variables is Boolean. So in a Sudoku problem, a square can contain 9 different values. So the way I am translating that into Boolean logic is I'm saying, okay, we'll have a true variable for each possible number that can go in each square. So we have a 9 by 9 grid of squares, and each square contains 9 variables for the possible states of that square. And one of them should be true. So the first thing I do here, you can see I scan over my grid. N2 is my, so my Sudoku rank can be 9 or 3. It can also be 2 or 4. I can make my boards bigger and smaller. But when I scan over my board, I look at each cell and I create a list of all the variables, and I say I want exactly one of these variables to be true. Now how that works is underneath FATSAT exactly 1 is saying, well, I want at least one of those variables to be true and at most one of them to be true. And those then are just Boolean logic. Now, it's Boolean logic built out of constructors rather than, like, I don't get to write x1 or x2 here, which would be nice. But I don't get to write that because I'm building it into a data structure. So I'm saying, like, well, grab this variable and OR it in, and grab the next variable and OR it in. So the at least one is this chain of variables ORed together. The at most one is a chain of pairs where I'm saying I shouldn't ever have a pair that are true together. So it's like, okay, here are 2 different variables, vi and vj. Those are pulled from the same set. And then I say, okay, it should not be the case that here's the and, so this and this. Then I say not both of them, right? So not both of these variables, and then I combine all that together, right? So underneath all the high-level looking logic, it's all being constructed down into Boolean formulas. And then there's another step you should know about if you're interested in this topic. Once we have a big, interesting Boolean formula, we actually translate it to another kind of formula called a CNF formula. And the CNF formula is like a simplified equivalent formula. It has the same logical properties. So if the original formula was solvable, the new formula is solvable in the same way. And if it was unsolvable before, it remains unsolvable. It's equivalent, but it's simplified down. So the structure is less complex to analyze. Ooh, that's a really interesting question. Formentera8 asks, is there a way to know if something can be converted into a formula, i.e. to a logical expression? I think that is a really insightful question. And the answer is that the only way I know of is to get lucky and discover the conversion. So if you have a problem and you're not sure if it converts to a logical expression or not, then the only way to know that it can be done is to find the conversion. There might be some ways to know that it can't be done. So for instance, we were talking about this a little earlier in the stream. If you have an optimization problem, that does not suit the SAT solver. So an optimization problem is a problem, any kind of problem is something where you have pieces that you're like moving around and arranging, right? SAT solvers, the pieces you're moving around and arranging are the Boolean values. You can set them to true and false, and you're flipping them back and forth trying to find a solution. So that's the pieces you can rearrange. But there's no way to make an optimization problem out of this. You can't get better solutions and worse solutions. Either it works or it does not, right? Either it's solved or it failed to be solved. There are other kinds of problems where it's like, oh, this is scoring a 10, but if I tweak it like this, it gets a score of 12, and then this gets at a score of 13. Like, you're inching out more and more. That's an optimization problem, and SAT is not in that class. So if your problem, there are ways you could notice that your problem definitely does not fit SAT by noticing that the kind of problem structure you have doesn't suit what SAT solvers do, which is SAT solvers are constraint problems. They rearrange the pieces trying to make all the constraints happy, but they either work or they don't. Either all the constraints are happy or they're not. There's no optimization, right? So there are ways to rule it out, but I think that the question, how do you convert a problem to SAT, or how do you know if it's possible to convert a problem to a formula, is that you have to study your problem. Right. So there is, JVS Tech is saying that his understanding is that there is some way that you can convert any problem to a SAT problem, but it depends on how complex you want the formula to be. Um, and that's pretty much true. Like, even what I'm saying about optimization problems could be made false if you're willing to run the SAT solver multiple times, right? You could say, come up with a formula that will calculate a Boolean, come up with a Boolean formula that will encode the way that I arrange my pieces to solve a problem and score it in the Boolean formula as well. And then set a constraint that says I want a solution that is greater than this threshold. And if it solves, then you go, oh, well, it can optimize at least that far. Then you raise the threshold and run it again and run it again. So if you're willing to run it multiple times, then it can do anything. But you got to be careful, because if you're willing to run it multiple times, then what are you doing outside of the SAT solver? The more you're doing outside of the SAT solver, the more the SAT solver isn't doing the solving. So I think if you want to be very specific about what SAT solvers can and can't do, you should constrain yourself to what SAT solvers can do in a fixed amount of runs, into a fixed formula, right? It's like, I'm going to run once and here's what I'm going to do. Or I'm going to run once and only once. If that first one succeeded, I'm going to run again this way, which is kind of what we were doing when we started this conversation, right? So there's like, the more flexibility you put in the code outside of the SAT solver, the less the SAT solver is the thing providing the solution. So can SAT solvers be used for anything? Yeah, sure, because you can put anything inside of anything else if you want. But if you want to really study what the SAT solver, where it gets its leverage, you want to study what it can do when you only get to run it like once or a fixed set of times or something like that. Flexin, yeah, my archives, you can find all of them. You can find my archives right here, Mr. Fourth Dimension on YouTube. I archive all of my stuff. So you come over here, you can see we did SAT solver. Here's where we wrote the core of the CDCL algorithm last time. SAT solver writing the naive conversion to the CNF SAT. Here's where I did some pictures of the SAT solver that might be interesting to see, reading the mini SAT code and stuff. So that's Mr. Fourth Dimension on YouTube. Yeah, it's interesting because SAT can be quote unquote used for anything, is a useful statement in the sense that SAT, there are lots and lots and lots of hard problems that map onto SAT. It's actually like there is earlier Formenta said there must be a science for this. There is. That's like what theoretical computer science is. The study of P versus NP all basically comes down to the discovery that there's this class of hard problems that if only you could make a fast SAT solver, you could solve all of them. And the fact that we don't think that P equals NP is the same as saying that SAT solving will always be difficult. Flex, and I thought my YouTube channels are linked together, but maybe they're not linked together in a super visible way. Do you mean they're not linked together on YouTube, or do you mean they're not linked together on? They're not linked to Twitch? There's a link on all of my YouTube channels to the other ones for sure, but they're kind of maybe buried. I could bring them to the top or something. Anyway, let's do this. So when we need to learn a new clause, I want to cut off. Okay, so that goes on Scratch. That is the deduplication helper. That goes on Scratch. All of this is definitely part of learning the clause. Backtracking isn't part of learning the clause. So here we want to bake the learned clause. And I think we put that into the output arena. We're saying, hey, whatever arena you gave me, that's the one I'm using to actually give you the final clause. We don't want this. We don't want this. Okay. Okay. That's it. So that's, hopefully that's a good place to cut it off. And then I will zero out all of this and then start saying, okay, so this much, well, reconstruct this chunk here. So we want, when we, oh yikes, let's turn off my search. When we learn, let's go to the learn function and make it match. So this here needs to be the CNF clause. And this needs to be the arena. There's also other stuff that is missing here, but we'll get that when we do the compilation errors in a minute. So when we come here to learn, we want to run the learn clause function here, and that gives us our learned clause. Right, so here we go. We try to learn a clause. Now, after that, we can do the backtrack. That's changing the order of things a little bit, but the baking and the backtracking can go in either order. So then we backtrack. We need to get the backtrack number, which is going to be determined somewhere else, I guess. We have to figure out where the backtrack number comes in. Guess number, CDCL backtrack, good. We want to save the learned clause into the formula. So this is where I think we want to learn the clause into Scratch, because what we were doing was formula. Oh, we're copying formula. Let's copy the formula onto the Scratch arena. And then when we learn new clauses and attach them, we're learning the new clauses onto the Scratch arena. So that can be like this. Learn the clause, backtrack. Let's do this. Learn the clause, log the learned clause, make a deduction from the learned clause. So the deduction literal needs to come out from the learning as well. We don't need that because we're not ending temp, and then we go to propagate. So that should mostly work, except for all the stuff we skipped. So backtrack number. Yeah, backtrack number, loose clause, and deduction literal. The loose clause is going to get baked right here. So the only trick is that learn needs a better return. Well, it's also going to need to see the CDCL at the very least. All right, we know it needs to see the CDCL. We see that. Now the question is, what does it want to see here? Assignment. Let's say type def struct FATSAT CDCL learn results or learn info. learned info. And so the learned info will include the clause that we learned, the backtrack number, and what was that third piece? The deduction literal. Okay. So that goes, let's see, learn here, then learn goes here. Here's our clause. And so our result can be right here at the end. The result clause is the clause. The result backtrack number is the backtrack number. And the result deduction literal is the deduction literal. And let's see, how close did that get us? Pretty close, pretty close. Here's the learn info. And this is going to want to see CDCL now. Now, learned backtrack number, learned backtrack number, learned clause, learned clause, learned deduction literal, clause. And you want to see the CDCL conflict clause. Oh, okay. We'll get to that. Let me catch up. I know I'm falling behind on the chat, so let me catch up and then we'll make more progress. Patrick, indeed. I don't I never have to explain why I think one editor is better than the other. I just go like, well, I wrote it, so why would I use anything else? Yeah, Flexen. I think I can do something to rearrange the order of things and put the linked channels at the top. They used to be on the side. But as you said, things change all the time. Formentera asks, if I am not mistaken, there are a handful of base cases where a logical expression is always wrong, right? Correct? Like violating law of non-contradiction or something. Are the problems the solver run into is how to find the base cases because they could be hidden in the expression. Yeah, that's kind of a way to think about it. It's not going to literally show up in the expression. It's not even going to be the case that you can directly see the contradiction in the formula by just taking the right snippets and putting them side by side. But what is buried inside the formula is very complex patterns of contradiction. So that it requires some work to uncover and see that it's a contradiction. And so the how do I want to describe that can happen? A direct contradiction is very easy to spot. Like if in one spot it requires that a variable be true and somewhere else it requires that it be false. That's pretty much always what a contradiction means. It means that on one level, a contradiction means that no matter how you assign the variables, the total expression comes out false, right? That's a very clean way to think about it. But if you want to think about it as, well, we're asserting that it's true, and so that assertion that it's true is going to run into the law of non-contradiction if it can't be true. That's a fine way to think about it. It can be a little bit more confusing, but it's also useful. And when we're solving, what we're really doing is we are making deductions as much as we can, but where we have to, we just make a guess. And then if that guess leads to a contradiction, we roll back the guess and make a different guess. And so a contradiction in the whole formula can be something like, hey, at the beginning I tried setting this variable to true, and then I found a contradiction, and so I rolled it back. And then I tried setting it to false, and then it was working for a while, and then I made some more guesses, and then I found a contradiction, and I rolled those guesses back and tried going a different way, and then I rolled back farther, and I tried going a different way, and I kept, and after trying all these different paths, it turned out there was no way to make it work. And this ends up boiling down to you run into a conflict, and that a conflict which is not based on any guesses, right? Whenever you have some guesses, you find a conflict. You just roll back the guess, but eventually you start learning things because we're learning clauses. We start learning like, oh, this variable is going to have to be true. But if we later learn that variable also has to be false, then we have a conflict that's not based on any guesses. Then we know the whole thing is unsolvable. So that is how it works. I'm kind of not giving you the full story because the full story is just an algorithm. And if you learn the algorithm, it will make more sense. But that's as good as I can do to summarize it for you. But if you go back to my previous video, we were talking about my YouTube channel where I have archives. On the previous channel, on the previous video of the SAT solving saga, I kind of diagram out the algorithm and the flow through the different states. And you can see where there's this process of we run into a conflict, and if we are on guess level 0, that's the end. But if we're on a guess like 1 or above, like we've made some guesses, then conflicts go to this like backtracking process. And that might help you to see what I'm saying in a little bit more specific detail. Okay, so in order to do the learn part, we need to pass in the CNF clause. That created the conflict. Also, I'm going to give you guys a YouTube recommendation that's not me, but let's see, SAT solvers. Yeah, this guy here. So I watched this video sometime in the last couple of weeks, and I think this is just a super excellent introduction to the topic. So if you want to learn more and you want another kind of presentation style, this is a nice 30-minute video that kind of gives you a good overview of the various flavors of SAT solving. And I am doing CDCL, which is the kind he kind of ends up with, but like this is the most advanced version he shows. He alludes to stuff that I don't know about, like phase preservation or something like that, which there's more for me to learn. But yeah, the stuff I'm doing is kind of covered in that video too. All right, so here we need to provide the conflict clause. Okay, let's make sure we can still run our solver. And it still produces solutions. Cool. So we didn't break it by pulling out the learned clause, but that was nice because that way I can guarantee that the learned clauses are going on to the same arena as the formula copy. Okay, so that was a little bit of a detour to get that working. Now, what we were trying to do is say, once we've run this once, we build the formula, the CNF version of the formula, we get a solution. What we want to try to do is say, hey, is there a second solution? Check for second solution, right? That's what we were actually aiming for. So to check for a second solution, what we're going to do is, first of all, it only makes sense to check for a second solution if we got a solution in the first place. And then what we want to do is say, like, can I modify a formula by giving it a solution? So solution contains in it assignments for variables, If I were to create a clause for that and stick it onto the formula, it could look like this. FATSAT CNF forbid solution, right? So I'm going to give it an arena and a formula. So this way it can modify this formula by giving it more constraints. And then it's going to give it a solution, and that's the solution I'm going to forbid. That's the API. It's going to modify the formula in place by forbidding this particular solution. And we could also do this at the level of the SAT formulas instead of at the level of the CNF formulas. But it's so convenient to do it at this level for now that I want to start here. And maybe we could talk about going back and doing it, but like this is the level to do it at if you just want to easily get going and start forbidding solutions. And we could iterate this, right? We could do this over and over again and find all the solutions too. Like I get a solution, I forbid it, I run again, it gives me a solution, I forbid it. You could keep it going. It might at some point start becoming slower to solve this kind of thing, but if you want to generate several solutions and count them and see when it taps out, or see if like it goes beyond a certain points that you don't want it to, that would be pretty trivial to do by just sitting here and modifying the CNF like this, which is pretty neat. Formula clause F. All right. So the forbid solution is actually just going to be generating a clause. So we can use the same loose clause thing. Oh, let me get rid of this. This is the old version of the learn section. So we're probably going to want a scratch. And we're going to start with a loose clause. And then what we're going to do is we're going to iterate the solution. If the value we're looking at does not equal 0, then, oh, and also we only want to do all of this if the solution they handed to us was satisfiable. We can, there's nothing to forbid if it's not a solution at all, right? But once we start with this, how do we do? So I called that a part of CDCL, but that's actually wrong. So we'll change that. Loose clause. Yeah, we need to build the literal. Okay, so we start with the positive version of the literal. If the value has a negative assignment value, then we know that that means it needs to be negated in the Boolean logic. And loose clause add literal. And then we bake the clause here. loose clause. This goes into the permanent arena, not into the scratch. Good. And then after we've baked a clause, we want to do this. Push that clause into the CNF like that. Okay. And then I want to pop in over here and say, where's the loose clause stuff? Yeah. To do move loose clause out of CDCL group and into CNF group. Because it doesn't actually have any ties to the CDCL solver. It's just used by the CDCL solver, but this is actually a helper for CNF stuff. Okay. So, we modified the formula by forbidding this solution. Here we're going to try to solve again. So I'm going to begin my accumulator again. And I'm going to ask for a solution. And here I'm going to say here's our second solution attempt. And if we do not have a second solution, we'll do this, and if we do have a second solution, we'll do this. So if we have not got a second solution, we'll write no second solution, found second solution. Like that, maybe? Now let's see what happens here. Look at that. There are multiple solutions. Haha. All right, so second solution attempt. In the first solution, it does this. Now, we got to the point of having two solutions by modifying the board. I think it was like a 5 right here. Let me double check. Yeah, so if I put a 5 here, then we're expecting that would be like, there are multiple solutions on this board, you say. Interesting. So maybe it's not working. Maybe it gave me the same solution twice or something. Let's work on this. So let's see. Forbid the solution. Formula fix. So the question is, hey Flexen, I'm not gonna do that. I appreciate you looking for a resource for me, but I think I'm happy with the boards I've got for now. I don't think more Sudoku boards is gonna advance the project very much. What is going on here? Why would it... Is it possible? Okay, well, here's one way we could deal with this. Let's say we don't know if this board... Well, okay, there's two ways I could deal with this. I am thinking it might be a good idea to do it this way. Let's have it run once. It says there are multiple solutions. Okay, I'm going to grab a copy of the solution that it gave me right here and throw it into Scratch. So there's the solution it just gave me. Now what I'm going to do is I'm going to keep the same logic for the solves, but I'm going to have it grab the second solution. Let's define that out here. Okay, so if I got a second solution, then I'm going to build the board out of that. And then we can compare them visually and see if it's really giving me two separate solutions. Okay. Are these identical? 185763492. Those do match. 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 Yeah, so this is not correct. So somehow it's not succeeding at forbidding the solution. Let's go through that in the debugger then. Okay, let's take a look. Yep, Flexen, you guessed right. It's actually finding the same solution twice. That's what I was just ruling out by looking at the two solutions side by side. And in turns out it was indeed just finding the same solution twice. So for some reason, it did not modify the formula, or the modification of the formula didn't make the difference. So let's take a look. It's easy enough to check that. Yeah, the first one is a 1. Gotcha. Okay, so it does look like it's building a new clause here. And this loose clause is probably, yeah, look at that. It's got 729 literals. That's a monster clause. That might actually make it really hard for it to solve, just because it won't notice that, it won't notice that there's a problem until it's gotten all the way to the end, and then that clause will finally create a conflict, which will then force it to go all the way back and look around a different way for a while or something. I anticipate that it may get finally a long run when we put in a clause like this. Because its way of proving that there's one solution is going to be kind of funny looking. But the fact that it comes to a solution, if there is only one solution, it should find the conflicts pretty quickly too, I think. We'll see. If there were two solutions, then it could be a long time for it to find the second one. But I think if there's only one, or if there are many, it wouldn't be so long. And even then, if there are two solutions, it could probably just figure out to roll back. Its only guess is, the only guess where it would have, well, yeah, it'd have to find the right guess to undo. Anyway, let's take a look here. So the clause that we get back here looks good to me. We push that onto the formula. Yeah, so the formula just gets one bigger in terms of clauses. Its last clause is the monster clause now. And the formula we've got here, yeah, it ends with a monster clause. So I know what happened. Okay, I wrote the forbid solution function just a little bit wrong. Forbid solution, I need to actually do the opposite in the negation rule. I don't want to say, hey, if the solution was x1 equals true, then put a true literal in the clause. I want to flip it. If x1 was true, put a false literal in the clause. That should do the trick. Now, like I said, this might take a long time to run. I'm not sure. Oh, look at that. It's still fast. That's cool. But let's see here. If we go back to second solution attempt, does it ever backtrack? Yeah, it has to do 1, 2, 3, 4, 5, 6, 7. 7. It has to do 7 backtracks in order to conclude that there is no solution here. 1, 2, 3, 4, 5, 6, 7. Okay, so we did 6 backtracks in the original solve, 7 in the second solve. But yeah, so when I have it fully constrained, the solution is unique. Now, if I come into my board on the test here, and I remove one constraint and run, it finds that there are multiple solutions. And this right here should actually be a new solution, right? So this, I think, is the original problem solution, 186. Yeah, this is one of the original solutions. This is the original solution where there's a 5 there. But in this one, it's finding a solution where there's not a 5 there. So eliminating that constraint opened up a new possible solution, and that solution was only possible because of the constraint removal, but it can find it pretty fast, which is cool. And it didn't find the same thing twice because it was forbidden from doing that, which means somewhere along the way, it's probably gotta be hitting the monster. I think this right here is the monster. Look, x0, x1, x2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. They're all here. Every variable showed up for the conflict right here. Or for the learned clause, except for x2, 7, 2. No, that's not the monster clause. This is a learned clause, but it must have touched the monster clause. The question is, did it ever make a deduction on the monster clause? No, it doesn't look like it did. So what happened exactly? It's very curious. I'm very curious about this. It did make a deduction off of the learned clause, which the learned clause clearly is based on the monster clause. 6, 7, 8. But it's so long that it's kind of going to be a pain in the butt to actually like break it apart and see what it's saying. 12, 13, 14, 15, 16, 17, 18. Yeah, you see what I mean? Like, this is going to be a huge pain. I don't want to do it. So I'm going to stop in a second. But the idea would be that we would look through all of these and see if anything in here broke the pattern. So far, every row gets exactly one false. And the reason that makes sense is because each row corresponds to a single cell in the grid. And so 8 of the 9 possible values cannot show up, and one of them does in the first solution. And then we forbid that solution, so we're saying, hey, not any of these. Now, what we could do, right, so one thing we could do here is this monster clause, we're very directly forbidding the entire Boolean state. Like the entire state of the original solution is a bunch of Booleans. We could forbid it without having to reference all of the variables, but that's because we know about the structure of our particular problem. Right? We could say, hey, I forbid all the ones that are true, I forbid those from being true again. And that wouldn't necessarily work in general, because it might be that there's an alternate solution, like in the general SAT case, it might be the case that there are solutions where you switch some of the false variables to true and the whole thing stays true. Now in the case of Sudoku, in the way we structured it, that could never happen. But ideally I could analyze this whole thing and see it, but I don't think I'll be able to. The pattern break would be interesting because that would be where we could see what the learned clause, how the learned clause differs from the monster clause itself. It might also not differ from the monster clause, but if it didn't, it should have made a deduction on the monster clause right away. It must have changed something. I don't know what. 724, is that going to be the interesting part? 724. Oh, look at that. 724. 724 is missing. Okay, that's what you got to do. When you see a conflict, so it's saying backtrack and learn. This deduction here was the last thing before it went wrong. 724 is false. You can see here, 724 isn't showing up. 720 isn't showing up. What's happening is somewhere right about here, things got funky. 725, 723, 721, 719, right? A few things here Flex, an interesting question, so I'll talk about it for a minute. It says, could you make it so that it prints the reason of the backtrack and not just the whole clause? Or for the learn, something similar that it shows the minimal print for it. So the problem is that there's not really any way to simplify that I could think of. Like I don't really know how I would simplify it. I would love to do something like that. I don't know what I could possibly do. Like what I would need is a visualization, not just a print. But I need to get out of text land and start drawing the graphs and seeing if I could maybe make sense of it from that perspective. The hard thing is the reason for the backtrack is always the same. The reason for the backtrack doesn't look different from one case to the next, and all it looks like all backtrack, the only thing that causes a backtrack is one of the clauses, all of its literals are false, right? So in the CNF structure, what's happening is a clause is a list of literals. A literal is a variable that's either it's positive or it's negated version, right? So we have not at the very bottom of the tree sometimes, but not always. All of these are kind of like logically ORed together, so within a clause. And so all we need is one of them to be true. But if all of them come false, if all of the literals are false, then we need to look at the variables that we're assigning that make all of those come out false and change one of them. And the way we do that is we look at, okay, so 189. So if we look back at the last guess, we'll see that at 189, at this level of guess, we guessed that variable 189 was true, right? So then we made deductions from that, and ultimately we found out that that led to a conflict. The conflict being some clause in the system is false. All of the clauses need to be true, so that can't be allowed. So we had to backtrack, and in this case we backtracked just one level to where we had set 189 to be true before, and we're learning a new clause. And the new clause we're learning is going to teach us that 189 had to be false. So let's see. I'm getting close to 189 now. So maybe if I do continue, I said I would stop, but I'm getting the sense that if I do continue, I will reach the point where we can see 189's location in the whole thing. And then we might make sense of this a little more. Let's see. My macro is messed up. So here we go. We're getting real close now. We're just trying to get to 189 because that's the one that it flips afterwards. And what do we see? 189, 190, 91, 93, 94, 95. 194, 195, 196, 199. Right, there's a gap there. 197, 198 didn't make it in. So these are multiples of 9 all the way up to here. 197, 198, 193, 4, 5 is missing. 6, 7, and 8 are missing. You can see something complicated starts happening because all of a sudden a few variables aren't there. So it definitely seems like it hit the monster clause. But then 189, 90, 91, 92, 93, 94, gap, 96, gap, 97, 98, 99, 200, and then, yeah. So, and then we start getting more gaps. So those gaps are interesting because that's spots where the monster clause stuff got removed out. And I'll bet you if we look, these will correspond to other things that got set. Backtrack. And the reason I'm looking at all this, by the way, is just to give myself an intuition of how things flow when it hits the forbidden solution. So 180. What was missing here? 195. Yeah, 195 was a deduction. So all the things that were deductions are the things that will be missing from this learned clause. So the learned clause is basically going to, because it hit the monster clause, it took the monster clause, and then all the things that were deductions weren't interesting aspects. But 189, which it had guessed was true, sticks around. And is set to false, is forced false here. And then everything else that's in here, all the things that weren't deduced at this level, they're things that were already assigned previously. And so those things that were already assigned previously remain assigned, and the things that were in the monster clause that got deduced in this get removed, so that that clause has a bunch of false and one free variable, which sets 189 to true. And from there, I don't think we see the monster clause again. Let me just, I can scan this way to see, but yeah, no. We never see the monster clause again. it just carries forward to a solution after that. Yeah, so Flex, and when you go and look at how the CDCL works, it'll clear up for you a little bit, but I can give you a basic walkthrough here. So we made a guess. It turned out that this guess, after we run some deductions that follow from that guess, is going to lead to a conflict, and a conflict happens inside a clause. A certain clause gets to the point where all of it is false, and that's not good. When that happens on the monster clause, we then are going to create a learned clause by looking at all of those literals in the learned clause, and since we had a conflict, they were all set to false. Like all the literals in the whole clause were set to false. None of them were left free, or else there wouldn't have been a conflict. So since they're all false, and it's the monster clause, it means every variable was assigned, right? But some of them one of them was the guess, which led to this mistake, and the rest were deductions from that guess. All of these, when we make the learned clause, what we're trying to do is simplify. We're trying to make a clause that is simpler than the one that was in conflict, in the sense that it would have been possible to avoid this mistake if only we had the learned clause in the first place, right? The learned clause is like a new piece of logic that is logically necessary given the rest of the problem, but which contains a hint that we were missing when we made this guess. And so once we have learned it, you can see we immediately deduce that 189 is false. So the only thing we have to do is say, okay, well, none of the things we deduce from this are necessary. What we've learned is everything we knew before this guess forces this variable to go the other way. And so we create a clause basically that does that. So all of the variables that are still here are the ones that were assigned previous to this. And then the one variable, this variable itself also shows up there. And what you'll see is, like, we look at, let's look at 224. 224 should be in here somewhere soon. Right, here it is, 224. So 224 is prevalent, is available here true. It is set true, which is the opposite of this. And then we look at 189, it's set false in here, or it's negated here, which is the opposite of this. And so you can see that this set of literals were all false when we hit this, this learned clause. Before the backtrack, all of those literals were false. After the backtrack, we've only changed one of the literals that appears in this clause, right? Because like I said, all these deductions do not appear in the learned clause, but the guess does. So the only thing we've unrolled that is appearing in the learned clause is 189. We made 189 free. And so this clause immediately constrains 189 to be false. Yep. So anyways, this is cool. It works. Let me take a look again. I think this might be a good place to wrap up for the day, but I would like to take a look. So we were taking a minute to say, do we have a way of checking for second solutions? So the way we did that was we took a first solution, modified the formula, and then we ran the solver again. That seemed to just work. Like that, it seems like a perfectly fine API. If you didn't bother with logging at all, what this would look like is just this, right? Boom, there's your second solution. You took an existing solution and the formula that you used to get it and the fixes that you used to get it. You run this one thing to modify the formula in place, and then you run the solver again, and it gives you a new solution if possible. Now, that's cool. The only thing is we might want to think a little bit about how we could simplify that clause, and that might be a good thing to do next time. So when we generate this clause, what we're doing is we're saying, hey, let's just not this one. This is the learned clause. The clause we put here was just the negation of the entire formula. It said anything we did last time, make one thing different, and we're good to go, right? Make one Boolean different. But if we then took that clause and we looked at how it relates to the rest of the structure of the problem, it might be possible to simplify it down. Because like if we looked at what we had here, right, and I'll cut it off to like here to talk about it. So each of these represents a cell, and we're saying, okay, well, in the first solution, 1 went here, and the rest of these, this would have been a 2 in the top left, a 3 in the top left, and so on. So all of these were false. This was true. In the clause that forbids this solution, we've got all of them, but we really could get away with just this, right? This would be enough. If this is false, if we force this to be false, that would be enough to ensure we get a new solution, right? And so my question to myself, I guess, is like, okay, if we look at, I think it shows you the, well, it doesn't show. Let me come up here. I'm going to say that logs the SAT. Here we can log the CNF formula. I'm actually going to do that again here. So after we've done this, we can log the CNF formula again. And let's run it that way, right? So when I look at my run log now, I've got my CNF formula, and then down here, so there's, I'm gonna wipe all of this out. There's the original CNF formula, and then CNF formula again. If we skip down far enough, we find the monster clause, the real one. Right, this is, or the forbidden solution. Okay, I'm going to use a single panel for this moment. So let's see, that's fine. That's fine. 0, 1, 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. See, I'll just grab a few of these lines and call it good. Boom, boom, boom. 1, 2, 3, 4, 5, 6, 7, 8, 9. Boom, 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 boom. And we could keep going if I stopped to align everything this way. Boom, boom, boom. Boom, 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 boom. Boom. Boom, 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 boom. Oops, that doesn't look good. Let's do it this way. Boom. Ah! Go away. What is this? Get me back to scratch. Boom. Boom, 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 boom. Okay, pretty good. Yeah, Flex. And so each time you make a solution, you would save it, and then each time you modify the formula, you're modifying it in place. So you could keep forbidding more and more solutions if you wanted to like generate a bunch of solutions. Totally. But on the other topic, I can't just say keep the negated literals. That would be true for Sudoku, but it wouldn't be true for SAT in general. So what I want to do instead is think about if there is a generalized way to think about this. And I'm going to do that by looking at this section for a minute. All right, so if we look at, here's a part of the formula. And let's see, I want to get as much of it on screen as possible. Right, so here's a part of the formula, and here's the top of the forbidden solution. we can see that, like, this is the pattern exactly 1, right? And so I guess what I'm thinking is, like, is there any way to notice by looking at this and this that we don't need these? Is there any way to use this to simplify this away? So if I have this and I put in not x0 and bake it down, what I would get is, okay, not x0 means this clause becomes equivalent to this, and these all become satisfied right away. So if I were to do that, then I would see this, right? And I would see that that is the same as this. So this being true implies this, right? So the idea could be, hey, if I have something in here that says not x0, and I see here I have an opposite, so not x0 appears here, x0 appears here, then the rest of this clause does not need to appear in here, right? Because not x0, if we got that true, then this clause, which is already in the formula, would carry the same meaning as all of these. Now what if, but that's only, yeah, I'm only noticing, so if x0 is true, then I just don't compare it to this, right? So if the fact that not x0 appeared in the solution is why I'm thinking about it. If x1, if we look at the x1 case, I was like, well, let's simplify x1. Let's use x1 as a pivot for simplification. Then we go, well, this and this match, so that's not relevant. We go, oh, this x1 is true and this is x1 is false. So if x1 is true, that implies that x0 is false. And so then this would become irrelevant, right? And that would be the same for once we have a duplicate here and here like that, we could eliminate this. If we use x2 as a pivot, we would again learn that this could go away. But if I use x1 as a pivot and I come here, then I learn that if x1 is true, then x2 is false. That is not the same idea as what's in here, so it's not redundant. Flex, and I'm not quite following your thought process. Technically, you can remove all variables up to the negated variable. No. So I'm not saying I can remove everything to the right of it. What I'm kind of getting at here, because like here in this case, I would keep x13. No, I would keep the negated, right? So if I wanted to simplify this solution, because I know how Sudoku works, I know that this would be good enough, right? I could keep these. And I know that by keeping these, it would force a new solution. But it's not good enough to force a new solution too hard. Like if you're too strong, like, so here's what you could do, right? Let me take you through the thought process another way. What if I just said, well, let me look at my solution. I ran without forbidding any solutions. I didn't do any forbidding, and I ran my first solver and got a solution. And then I looked and said, oh, look, x0 is true in my solution. Well, then let me just tell this thing, run again, but now it has to make x0 false, right? So if I did this, what would happen? Well, it would do one of two things. It would either say, ah, yes, there is a solution where x0 is false, and here it is. Or it would say, I can't find a solution. But the problem is, if it can't find a solution in this case, that doesn't mean there are no other solutions. It just means there are no other solutions where x0 is false. Does that make sense? If I'm too narrow, if I make it too narrow, my forbidding clause, then I might be ruling out solutions that are possible that I'm interested in. But if I do it this way, then then it's just super wide. So the question is there a good way to simplify this? So this is forbidding the whole solution, but I know, for instance, that if I'm making a Sudoku solver, that I don't need to specify all 9 of these or all 9 of these. This is enough to imply all of these. This is enough to imply all of these. So I think the way I would simplify it, I think the algorithm would go like this. First, we want to pick a pivot, and we're going to set aside the question of how you pick a pivot. Once you pick a pivot, the pivot is one of the literals in the solution clause here. And you say, okay, so x is not 0 in the solution, in this forbidden clause, right? In the forbidden solution clause. X is not 0. So I want to look for a large clause in the original formula where x0 is the opposite valence, or it's the opposite polarity. So x0 is negated, x0 is non-negated. And then I would say, okay, so mix this with this. And what do I learn? Well, I learned that if this was met, if x0 was false, then this clause would already imply, x0 being false implies x1 or x2 or ... or x8. And so x0 being false and one of these being true, x0 being false or any of these is redundant, right? Because once we satisfied this, we would have satisfied these. Now, the problem is I know that works in the Sudoku case. I'm trying to think if that works in general. I'm not sure it does, because it could be in a general SAT problem that that you keep x0 true. And so is it possible that x0 being true is interesting because of these? If x0 is yeah, I'm getting a little lost in it. I'm not quite sure if there is an easy way to do this. I'm sure there is a way to simplify clauses. I know that's a thing, but I don't know if there's a way to do it outside of like finding a conflict or something. Like in the CDCL solver, there are algorithms for simplifying a clause, but they kind of rely on the assumptions that you have while you are running the CDCL solver that give you the ability to infer relationships between things. I don't know if I can do it just from scratch quite as easily or using the same techniques. Because what I would like to do is be able to take this information here and combine it with this information to make this modification, if that is possible. But then that makes sense as a reduction on the pattern of one of, right? This is the at least exactly one thing that we built earlier, right? It's an OR of all of them plus the pairwise negation of them. And that means all you have to do is negate the true one from your solution, and you've enforced a new solution. Well, they're all going to look the same. Like the next part of the formula, let me show you. The next part of the formula looks like this. They're all the same thing. So here's the one for line 2, right? x13, x13. The only difference is in the solution which one's going to be negated. The rows here are going to have the exact same structure here over and over again, because these are generated super mechanically. The rows are all going to have one negated spot, and that's the entirety of the structure. There's nothing else to see. I think a part of the hard thing here is that I'm looking at Sudoku and I'm using my Sudoku brain, and I would need to get to the point where I was using my SAT brain. Like, instead of looking at this like this, what if I did more abstract, like we run a, I'm gonna wipe this out. I'm just trying to think if there's a way to do this simplification that I have in mind, or if there's some way to find a simplification of the forbidding clause. So say we have a solution, then a solution is like a bunch of these assignments, right? Etc. The easiest thing to do is to encode the negation of all of these. Then the other thing you could do is you could take them one at a time. You could say, okay, x0, what if I set x0 to false? And see what that implies. So like x0 equals false implies what? And then I look through my formula. For every occurrence of x0, okay, maybe there's another way to think about this, right? Say I did this. Say I looked at, let's back up. I have an idea. Maybe the right way to think about this isn't as comparing two clauses, but as redundancy checks. So let's say I look at x0 and x1 and I ask, is this redundant, right? That might be a thing I can answer, because I might be able to go, okay, if does one of these imply the other, right? Because if we think about this more like logical operations for a minute. So if this is our, let's just call these A and B. So not A or B. And then let's say we go somewhere else separately. We learn that, so this is our formula. And then from outside constraint, let's call this an outside constraint, right? We want to say, or let's call this our clause, and we'll say we have an outside constraint that B implies not A, right? Then B implies not A is, by the way, the same thing as this. Just a disguise for that. So the question is, right, so what this line of thinking would do is I'd say, hey, are these two redundant? A and B, are they redundant? And we'd learn that, well, if you have B, that already implies not A. But it's not necessarily the case that if you have not A, that implies B, right? That's the reason it doesn't quite work. Instead, we have another clause that says that A would imply not B. But that's, I mean, that's just the contrapositive of this. That's not interesting. It's not useful. The fact that these are redundant is really only visible, something you can notice by analyzing all of this together, right? Because what you basically see is that you go, oh, we have something like this, right? Say this is our clause, and we have B implies not A, C implies not A, D implies not A, and we have not A implies B or C or D. Now it's interesting because then you can start to go, well, hold on, what we're saying is B or C or D implies not A, right? That's what all of these separate things are saying. And so once you have this if and only if relationship established, then they're redundant and you can take the smaller one. But how do you establish an if and or only if relationship when you don't know which combinations to look at? Like, how do I know that I look at this one and compare it to these 8? Doesn't seem trivial to figure that out. I mean, it's pretty clear in this pattern here. And so I could try to make a pattern recognizer that's like, hey, if you see a clause of 9 followed by, 9 choose 2 clauses of 2, then take a look and verify that that's a one of pattern. And then when you find all 9 of them in your solution, keep that one, right? So that's a way I could do it. I could be very direct. But I would also be relying on these being in order, which they could be. Like, it would be unlikely for them to be in a different order, but they'd have to be in order for me to recognize it then. It's no longer... Yeah, this is interesting stuff. Like I said, I think I'm going to wrap up here. I'm not seeing any obvious way to do it. This is a cool capability we added, the ability to find secondary solutions, but trying to make it smarter feels a little difficult for me. Trying to make it smarter at the level of a SAT formula feels difficult. Trying to think. Yeah, I maybe want to do some research on this next time. So let's take some notes, things to do for next time. Actually, let's fix that to do that I just spotted before we call it a day. We'll do that. So these are in the wrong spot. We want to have them come up here and live with CNF. Okay. All right. But besides that, we have a new question there. High-level constraint writing APIs. I think we still need to come up with more use cases to explore further on this front. And, I said I wanted to wrap up, but there is something I would like to do. I would like to modify the SAT formula that we start with. So we did the bit where we plug in numbers, but let's do an empty board again, and let's come up with an additional constraint. So Sudoku by itself has some rules, but another rule we could add is a king's move constraint. So the king's move constraint says that a number, each cell, whatever number is in it, should not be a king's move away from an equivalent number. Now, there's only a few ways that can even happen in Sudoku in the first place, right? Because you can't have, right, if you have a king's move, that's like this, right? So you already can never have x's here, right? At this spot here, it doesn't matter. At this spot here, it doesn't matter. At this spot here, it doesn't matter. And at this spot here, it doesn't matter. And these stars here are sometimes also impossible. Like if we're in the center of a box, then this is already enforced. But if we're on an edge or a corner, then some of these stars might be constrained by this rule when they wouldn't be in normal Sudoku. So how can we implement this? Well, we could just implement the whole, we could go through every cell, look up, down, left, and right at all the 8 neighbors, and unless those neighbors go off the grid, we generate a constraint for all of the possible numbers that go in them. Or we could simplify and say, look, we don't want a constraint. Like if I have a grid and I have, x and y sitting next to each other like this, I don't need them both to generate a constraint. X can generate a constraint for y, y could generate a constraint for x, but they're both going to be the same constraints. They don't both need to go. So instead what we could do is say, okay, you're going to handle those spaces that are up and to the right of you, right? And if there's something below you, it's going to handle the constraint with you. If there's something to the left of you, it's going to handle the constraint with you. You're just going to handle up and to the right with you. And we already know we don't need this or this because the row and column constraints are handling it. So really, for each cell, we look up and to the right, and that'll be the whole thing we have to do. If we wanted to, we could say, let's do all of them, all 3 of these, even though these 2 are redundant. And the reason we might do that is to say, well, what if someone wants to use the king's move constraint in a board that doesn't use the column row or the column constraint or the row constraint in the normal way? And you could do that, but for now I won't. And so now all we have to do here, like let's come up with a good way to mark these things. This is our center point, and we're just interested in the these here are sort of the ones we're ignoring. We're just interested in the star, right? So for each y value, we don't need to start at 0 because the top row won't have anything above it. So 1, y less than n2, y plus equals 1. For each x, using the same rule, we get we want this right here. So here's my cell index. And then I want star cell index. I'm realizing this can't quite be correct. And let me tell you why I think this can't quite be correct. How will these two ever create a constraint between them? I think I can't eliminate vertically and horizontally, right? I want to make sure that there's a disambiguation, but I don't want to lose constraints. So I think I actually have to do these two stars, right? This will handle its constraint with me. I have to handle my constraint with everything to the right of me and everything in line with me. Now these would, right, if I didn't have, let's take out the big X's here. So if I was trying to figure out how to do this, I might say that the pattern would be like this, right? You handle everything to the right of you, and everything that's to the right of you, no matter what its Y value, and everything that's above you that's directly above you. So you do this, right? But then this and this are handled by the row and column rule, and so we just do these two. So this is if why don't we just do the whole range? I think that'll be easier. So this is if X is plus 1 is less than N2, and Y is greater than 0, then star cell index equals N2 times X plus 1 plus N2 times Y minus 1. And then what we want is a new constraint that says it's not going to be exactly one constraint, right? Because we're not saying there should be exactly one of these. Rather, we're just saying in this pair, they should not be equal, right? And the pair is 2 cells. Each cell has an array of 9 variables. So it's an at most 1, right? For each number, right? For the number 1, there should be at most 1 1 in the pair, and so on and so on. So let's just write this like this. Let's do convar builder cell index plus I, right? We need to do a loop over the i's. So we grab the variable, we grab that variable, and then we're saying so the helper I want here is going to be a little simpler. This is like saying it's like saying at most 1, but it's just the case where there are 2 things. So this can be like FATSAT con not both, and then you go arena builder Okay, this has got my brain turning again. I can remember a few other helpers that I know I want. So not both is going to be built like this. C0, C1, both. Take the not of that. Return not both. And so this can now be FATSAT con not both. Arena builder VI VJ. So not both VI and VJ. Thanks for hanging out, Flexin. Have a good time sleeping. And thanks for hanging out. All right, so there's our not both. I might also want just some other basic stuff like FATSAT con same. So this would be like FATSAT con same structure as this in terms of interface. But to make these the same, we want thanks, JVS Tech. Both true, and then there's going to be both false, which is going to be a little interesting. We need an N0 and an N1, which are made out of the negations. Arena builder C0, C1, N0, N1, both false. And so then our result is the and of both true, or is the or both true or both false, right? And then an XOR one we definitely want. An XOR can be built, we could just do this as negation of same. That's one option. XOR could also be, we pull out N0 and N1, and we could be like B0, B1. So this would be C0 and N1, or N0 and C1. And then this is either B0 or B1. So branch 0 is C0 is true, N1 is false. B1 is N0 is false, or C0, yeah, and we got two things, C0 and C1. One of them needs to be true, and one of them needs to be false. There are two ways to do that, branch 0 and branch 1. So we take one of those, and then this is XOR, right? So those are some reasonable helpers to have. Okay, so now we have new rules here, which just say FATSAT con not both, scratch arena builder root. Oh, FATSAT con so not both is going to be C1 and C2. FATSAT con not both. And then we chain all the not boths together like this. Root not both. So there's our x to the right and y up 1. And then let's also do x to the right and y down 1. Let's rearrange this. So we'll do the loop once. We'll do C1 once. And we'll do this if in here. And this and this in here. So for each number, yeah. So we iterate x and y, grab each cell index, grab each I value, or each cell number, and then we grab those star cells, which are the diagonals from us, to the right, the diagonals to the right. The diagonals to the left will reach in and talk to us. The rows and columns will handle these. And so this should implement a King's move constraint into our board. Oh, and let me change my logs again. So I do not want the C and F logs anymore. I don't want to check for second solutions anymore. I just want, yeah. One, two, three, four, five, six. Now I don't know if this constraint actually modifies the board at all. There might not have been any violations of the King's move constraint in the board it would generate. So let's turn off the King's move constraint, run, grab the board, save it, turn on the King's move constraint, run, grab the board, and compare 4, 5, 6, 2, 1, 4, 3, 2, 1, 4, 3, 6, 5, 9. Ah, this is different. Do you see this? 9, 7, 8, 9, 4, 8. There must be, right there, King's move constraint got violated in the first run, but in the second run, it didn't violate the King's move constraint. It put the 7 there and the 4 there. That's cool. That's cool because, like, you can start to imagine, like, what if I had a UI for this and I could start toggling my constraints and be like, okay, turn on King's move constraint, please. And then it would turn on King's move constraint and rearrange your board for you automatically, or like say, nope, now it's not solvable, and then turn off the other constraint. So let's play with this a little more, because this is giving me inspiration for patterns that I want in the API still. So there's King's move constraint. There's another fun one. Similar starting point. Called the Knight's move constraint. And the Knight's move constraint says well, let me start with a board here. 4, 5. 1, 2, 3, 4, 5. Here I am at the center. Whatever digit I put here, I am forbidden then from putting it into any of these locations by a Knight's move constraint. Now these are way wackier. They are not captured by row or column rules, and most of these cannot simultaneously be captured by a box constraint. It's possible for this to be the corner of a box, and then one of these pairs is captured by box constraints, but whichever corner it is, unless it's the bottom, like the absolute corner of the grid, the other ones still kick in and do something funny. So again, I want to put in a rule that says, okay, These ones here, we don't need to worry about. They will reach in and talk to me. So I'm going to be handling these ones. So that's like this. If x plus 1 is less than n2 and y, we have to subtract 2 here. So y has to be, let's rewrite this as y is greater than or equal to 1. Then this y has to be greater than or equal to 2 because we have to be able to subtract 2. So then our star cell becomes this. Now we're starting to see this pattern, which might be a Sudoku pattern, of we grab two okay, so this is not a general SAT thing yet. I don't think it will be one, but we want like a Sudoku constraint, not both, where I can give it the arena and the constraint builder, and I guess the root, and then 2 cells, right? So a Sudoku constraint called not equal, where I give it 2 cells, and then it does something like this, I guess. C2, C1, it does the loop over all the i's, returns the new root when it's done, arena builder, root, cell index 0, cell index 1, and yeah, I have to give it the rank so that it can do that calculation. And then it can do this loop, grabs each variable in the cell, in the 2 cells that I gave it, and makes those cells not equal by saying that they cannot both have the same value. Adds that into the chain here. Yeah, okay. And so then the king's move constraint can be rewritten as Sudoku con not equal. I don't need the I loop anymore. I just do the not equal right on the root. I give it the Sudoku rank n, and then I give it cell index and star cell index, right? So that goes there and there. So that eliminated the I loop and the 3-4 lines it takes to put those pieces together and replaced it with a single function call. Now, the other thing I could do to make life easier here is to just say, oh, but then I'd have to do x's and y's. So this could get a little bit better if I was passing the x's and y's in instead of the cell indexes. But it would mean more parameters. But like I could go x, y, x plus 1, y minus 1. Right? Imagine if this just could say x, y, x plus 1, y minus 1. And then it wouldn't have to do any of this. Right? That seems like a huge step forward. So we're going to go x0, y0, x1, y1. And we're going to compute cell indexes. Cell index 0, cell index 1 from those. But we want to check, just lightly do like a safety check here. These need to be inside the legal range, right? If x0 is less than n2 and y0 is less than n2 and x1 is less than n2 and y1 is less than n2, then we go. But if any of them got outside of the range, then we just ignore it. We say, yep, that went out of the grid, irrelevant. And then we specify these constraints now by just going x, y, x plus 1, y plus 1. And we're relying on the fact that if this, we're relying on the fact that n2 won't be so large that rolls over into a valid range, like valid number again, right? If we are making grids where we're subtracting or adding like 100 and it happens to be that there are like billions of cells, then that would be very surprising, right? We're expecting 4s and 9s, maybe 16s here. So rolling over a U32 should put us outside the valid range. Okay, so then a knight's move constraint is just 4 of these. X, y, x plus 1, y minus 2, x plus 2, y minus 1, x plus 2, y plus 1, x plus 1, y plus 2. All right, so let's first check that the knight king's move constraint's still doing the right thing. Oh, yeah, you need me to return the root not equal. And these need to actually capture the root that comes back. Okay, when we run that one, we still get, yeah, it still avoids this king's move constraint violation. That's cool. Now let's turn on knight's move constraint. Runs, comes up with a new solution. Let's take this over to Scratch and see if it, oh, let's take Scratch back to there. Did it modify? 1, 2, 3, 4, 5, 6, 7, 8, 9. Still valid starting, apparently. 4, 5, 6, 7, 8, 9, 1, 2, 3, 7, 8, 9, 1, 2, 3, 4, 5, 6. So that's all the same. Ah, here it's different. 2, 3, 4. So this one and this one are in conflict. So it's changing that to a 3. 4, 5, you can see those were in conflict and these were in conflict. So yeah, it's shifted these all around to avoid that. I'm curious when it solves this back. Hold on, really? You're telling me you do the whole thing flawlessly by deductions and guessing. I mean, I guess that's not crazy. If there are more constraints, maybe the deductions guide you better and you have less trouble. I'm constantly surprised how easily it solves these. I did not think it would be possible for it to go that fast. With more constraints, I would think it would hit mistakes more often, but in fact, it's making deductions more often and avoiding mistakes. It's really cool. Okay, so we have standard or classic. Here we have king's move constraint. Here we have knight's move constraint. All right, what else could we do? So another style. Let's look up a right. Okay, so here are some fun constraints we could do. The I'm looking here and I'm remembering. So there's these ones that get placed in positions on the board that are these white and black cells, and I can't remember which is which. Maybe there's another one I could grab that would be a little better in my memory. Let's see. I'm gonna turn off my music so I can do this. Boom. Give me a minute. All right. I'm just gonna scroll through their. This channel does a lot of Sudoku puzzles. If you've never seen them before, it's one of the inspirations for this project that I'm on with the SAT solver and all of this. So I just want to see if they've got any on here that jump out to me as good examples of some. So that's thermometer, which we could. I guess thermometer would be a good one. There's a lot of thermometers in this one. Let's see. Digits along an arrow must sum to the digit. Oh, that's not thermometer. I don't want one with like lots and lots and lots of stuff. Thermo Sudoku. Okay. Okay, perfect. Perfect. This is exactly what I wanted. It's nothing but a thermometer puzzle. So the rule on one of these is that in addition to normal Sudoku rules, there are these thermometers drawn into the board, and the numbers need to be increasing along the thermometer. Okay? So at the bulb will be the smallest number, and as you walk along the thermometer, the numbers should increase. They should not be equal to each other. They should definitely not decrease. They have to be getting larger, okay? Now, this is cool because it's a blank board, but it's got these thermometer shapes on it. Now, these thermometer shapes, essentially what we need to be able to do is encode a less than, greater than relationship between two cells. So let's figure out how we would do that. All right, so it's going to look a lot like this in terms of structure because I'm going to want to pass it two cells. So I'll make sure those two cells are valid. I'm just going to return the root when it's done. Then what it's going to do is calculate the index on those two cells. And what we're going to do is say, okay, if this cell here has to be less than this cell here, okay, so how will we generate a constraint like that? Well, it means that all of the configurations where this is equal to or less than this have to be ruled out. So we're going to do a loop over the possible values of each cell separately. We're not comparing their same numbers, we're comparing different numbers. And so I0 will represent the number for the cell 0, and I1 will represent the number for the cell 1. Now the ones which we want to rule out are the ones where cell 1 is less than or equal to cell 0, right? So here we'll do a loop where we'll say, okay, well, what are all the cases where cell 1 is less than or equal to cell 0 when we have a value for cell 0 here, right? And then we'll grab these, but instead of having them be the same number, we're grabbing two different numbers. We're grabbing a number for cell 0, or a value for cell 0, right? And then a different value, possibly different value for cell 1. And it's guaranteed that these two should never go together by the way we've iterated it. So we don't want both of them, right? And then we spit that out into our constraint. So there's our less than constraint between two cells, right? Now, the tricky part is that we cannot just say that this is a generalized rule. We have to do it based on this pattern, right? This gives us a set of patterns. So let's try to figure out, using something kind of like the board trick, how we would write down thermometers. Gonna be kind of tricky and weird. I'm gonna do this in my notepad. Okay. We'll start with 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So how could I do this? I could use digits to link them up, but then I don't have a direction, right? I could say, well, hold on, let's point an arrow. So this has to be less than this. This has to be less than, how do I point an arrow down to the right? I don't have any great ideas on how to point down to the right like this, but that could also be up to the left. That's a little not good. What if instead of trying to do it this way, I say, all right, let's have a cell which, let's say it starts at 1, 2. Or rather 2, 1, x 2, 1, and then it goes right, down and right, down. I mean, that specifies the thermometer. So what I'll have to do is I'll make a, okay, I get the idea. So what I'll do is I'll make a, let's do side by side this way. Get out a full screen 4-coder, put these like this, and put my music back on. Okay, we're good to go. So each thermometer I'm going to specify like this. I start it at a certain point, P. And so the first one is going to be a 2, 1. And then I'm going to go scratch arena builder root Sudoku rank n. P is an in-out variable, and I have to give it directions. So I'm going to give it the direction 1 to the right and 0 vertically. Okay? And then repeat that, but now it's 1 to the right and 1 down, and then it's strictly 1 down. So there's my first thermometer, right? I give it a starting value and then a sequence of moves. I could also do that like this. I could do moves equals and then give each of them like this. 1, 0, 1, 1, 0, 1. So starts here, goes to the right, goes down and to the right, goes down. And then I could go thermo is, here's the P, here are the moves and the array count for all the moves, and have it do that. So you give it a start point and a set of moves, and then let it generate. Yeah, okay, that seems pretty good. So let's build that helper. Give it this. 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 This. And this. Okay. We can go back to full screen for a little bit here and split. We'll come back to the board in a minute. So what we want to do is for each move, we grab the move, we grab the next P, and then we're going to go Sudoku con less arena root equals arena builder root rank px py. Why don't we call this q instead of p so it'll fit nicer? Qx qy, right? So I take my p value, I grab the move off the list, and I get a q. That gives me a less than constraint, and then I update p to q. When I'm done, I return my root. Okay. So there we go. Hopefully that is all good. Go back to side-by-side mode with the board, and let's build the rest of these thermometers. So there's a thermometer there. 2, 3, 4, 5, 6, 7, 8. 8, 1. Moves to the right by 1, moves to the right and down, and then it moves straight down. So there's a thermometer. Okay. Now this thermometer starts on 3, 4. It moves to the left. It moves up and to the left and then straight up. 2, 4. 3, 4, 5, 6. It moves to the left, down and to the left, and then straight down. This one starts at 5, 7. It moves up and to the right, and then straight right. Okay. This one begins at 7, 8. It goes up and to the right again, and then straight up. And this one begins at 5, 9, and it goes up and to the left twice, and then it's done earlier than the other ones. Okay. Cool. All right, if y'all want to do this puzzle, then turn away because I'm going to reveal the solution. Oh, it's running slow. It's having to work. We found one that makes the solver work. Look at this. I'm jumping to the end, and this is what I'm seeing, which means it's still running. Okay, okay. It might be caught in the loop if there's a bug. Or the learned clause might be getting so big that it's not doing a good job of making progress anymore. I'm not sure. I also might have encoded the constraint wrong so that it's more complicated than it's supposed to be. But yeah, look at this. All right, let's take a look at... So here we are. It backtracked. It learned this x86. My run? Run is what do you mean does it auto jump to the end? Do you mean in forcoder it's not like constantly keeping the cursor at the bottom? Yeah, it's just like a text buffer that's growing, and I'm not watching it grow at the bottom. I'm exploring it as it's going. So what I was looking at is x86 here. x86 is false. Here it was true. And it hit a conflict, backtracked. Guessed 87 is true. Set 87 to false. Yeah, it's just guessing everything. Every possibility, looking for something that is not a contradiction. Yeah, so for coder, when you have a run buffer, it does not have to keep the cursor at the bottom. That's correct. I can't remember the setting for that. Like if you're asking me how to do it, I could go and look up, like, I think it's a custom, like, I think that's something you control from the custom layer a little bit, but this is default behavior for the run buffer. Because I don't use any customizations that aren't default. But wow, yeah, this is making it work hard. I can't tell if it's caught in a loop. Like here we are with x80. Let's go to the beginning and just look at what it's doing here that's causing it to spend so much time guessing these things in the 80s. It's working real hard. My computer's going slow trying to do this. So it guesses that. Oh, you know what's probably happening here? There are no heuristics for good guessing, and for the first time ever, it has no easy deductions to make. So it's really Oh, BYP, thanks. You know, yeah. I thought that was not customizable from the config stuff, but there you go. It is customizable from the config stuff. That's great. So it seems to me like somewhere here around the 80s, it started hitting trouble. Yeah, this is its first backtrack. And it's backtracking from the guess 104. So it says 104 false. Yep. Let's jump to the bottom again. Gotta wait for it now. But this is cool. If it does manage to finish at all, it'll finally have given me a good benchmark so that I can come back to this with questions about performance. It might also be, there's a possibility, I don't know if this is true, but it might be that we finally have hit a case where well, no, the transform didn't take a long time to run, so the transform isn't the problem here. 2, 3, 4, 5. These learned clauses are big, but they're not like extraordinary. They're not like the forbidden solution learned clauses. They're more like just standard Sudoku learned clauses. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. 28, so almost 3 big clauses. Almost 3 of the like standard Sudoku size clauses. Man, those are some big dudes that are making the deductions on. It's making deductions on right there, right? Backtracking again. Yeah, I think without heuristics and without optimizations, this one might not be able to watch it finish today. I mean, I jumped to the end, and you can see we're at about 100,000 lines. I could also turn off the logging, which might help it run faster. I could like turn off all the deduction logging just to give it a lot less printing to do. Let's try that, because often when you turn off, you turn down your printing level, you do get a good amount of speed up. That can take a lot of time. So just need to find FATSAT, kill it. We'll kill that run there. What we'll do is we'll come in here and say, okay, where? Yeah, let's turn this part of the log off today. Go. But you can see the guess number is moving all over the place, which means it's doing so many guesses that it has to backtrack. And that is the sign of a SAT solver having a hard time. It's not able to just find its way down the correct paths automatically. There's another thing I could do, which is to back off of solving this particular thermo problem and just write down a simple one, like on an empty grid, and let it show me what it does there and make sure that it actually like understands the constraint properly. I didn't put in something way more complex than I meant to. But this isn't that surprising. The less than constraint is like an n squared compared to a not equal constraint, right? Like there's a triangle of things that get ruled out rather than a single line. So the number of clauses is probably a lot bigger. They are learning so many clauses because of all this too that yeah. Tamwile, hello. Let's see where we're at so far. I'm able to keep up now. Like Forcoder is not crashing, or it wasn't never crashing, but like it's not stalling when I try to jump to the end. You can see we're still gaining a few hundred lines at a time, but it's not gonna, if I stop printing these, it's not going to make it so much faster that it happens automatically all of a sudden. Tamuel, you can find, if you're interested in my website, it's mrforth.com. All right. And if you go over to my videos here, let's say we go to this one and we go onto my channel and you scroll to the bottom, you'll see my other channels here. So Mr. Forth Programming is one of them. Mr. Forth Dimension is the VODs channel. where you'll find what you're looking for in terms of whatever VOD it was you wanted to keep an eye on. Man. But yeah, this is not looking good. I think the SAT solver is stumped on this one, and it might be a good use case for figure out why. Made a bunch of guesses in a row right here without a problem, but then you can see it's backtracking. Yeah, yep. Probably a heuristic would make a huge difference here. Because if I sped up things like propagation, so there are ways I can speed up propagation that would help. And there are ways I could simplify the learned clauses. So speeding up propagation would help make propagation faster, but it wouldn't change anything about how many backtracking and guessing steps it has to make. Simplifying the learned clauses could make a bigger difference, because that would actually change the patterns of deductions and therefore the point at which backtracks get discovered and the amount of work that goes into that, but it would still be minor because the simplified clauses would only lead to what's the way to describe it? It would only lead to slightly different backtracks, possibly fewer, possibly earlier ones, but usually just about the same ones, just faster to discover them. So to change the actual pattern of the search here, it would require me to actually build a heuristic for the guessing, which I haven't done. Right? You can see every guess is always guessing true, and it's also always guessing just the first variable that it can, which is not a good heuristic. It's just been good enough up until now, which has been blowing my mind. So I'm going to stop it again. Gotta refresh the list. It's under here this time for some reason. Sometimes it is, sometimes it isn't. You can see it did not finish. I'm curious if we compare the beginning to the end. Like here it's like guessing around 60s and 80s. Here 70, it's kind of in the same exact spot. Like it doesn't look like it made significant progress. So whatever it was working on, it didn't really seem to have figured anything out. So let's take a step back. Let's look at the thermo here. We're going to, this was the thermometer specific to that particular problem. And just to be sure, yeah, so our board is starting off blank, which is good. Let's put in a set of a thermometer that'll be simpler. So our thermometer that I want is going to start off at (9.1). It's going to move to the left. Whoops. So it's starting in the top right corner, and it's moving to the left 4 times. Okay, so that's going to be like let's look at okay. So that would be like a thermometer that starts here and then goes 1, 2, 3, 4 to the middle point. So this is going to make it impossible for it to go 1, 2, 3, 4, 5, 6, 7, 8, 9, and it's going to have to flip that around or something like that, right? Because it's going to want to put the small side here. If the rest of the board is blank, I think it'll still be pretty easy for it to find a solution, but it'll have to work a little harder to work its way through this thermometer. And we might be able to see why the thermometer trips it up when the other things that we've thrown at it so far haven't. Okay, still running. Yep, this is making it work too. Can it even solve this one? If this can't be solved, then I'm going to just give it a single less than constraint in the top right corner and see if it can handle that much. Yeah, it doesn't look good. Okay, let's say that's good enough to satisfy us that it's not going well. Let's back off again and just do a single less than constraint between x9, y1 and x8, y1. Right, so top right cell needs to be less than the cell to its left. Since what it usually likes to do is generate 1 through 9 on the top row, this should just force it to change that. But it should still be easy. Okay, so it did actually... Oh, it didn't work. Did I mess up the... No, so something's not working. Less. Okay. X0, Y0, X1, Y1. Cell index 0, cell index 1. C0, C1. C0, C1. C0. Why did I not make these names line up? That's silly. Okay. So let's see here. So when this is 0, this will go 0, it'll go through, we'll grab the thing and say they can't both be 0 because this has to be less than this, right? This cell has to be less than this cell, so they can't both be 0. But it'll leave the possibility for 1, 2, 3, 4, 5, 6, 7, 8, and then it'll come over here, increment this to 1. This will then look at the case where this is 0 and then the case where this is 1, and it rules out both of those. Yeah, so it feels like that should be working. The fact that it's not, and the fact that when I run this, right, it just builds the original board. It builds the board of, oh, you know what? Well, here's a problem. I had to turn off the king's move constraint and the knight's move constraint for one thing. Those definitely don't belong. Okay. So, yeah, that's just the original board. Now, something is wrong with this constraint builder right here. Oh. Right, so these need to go like this first. because we're entering them in the range from 1 to 9, and then we're not getting the constraint. So now, there we go. Now it is forced to switch these two around. Right. Okay, so let's build back up to the thermometer. So not the less than constraint. Give me this. Let's just say it moves twice, because if I move it once, it'd be the same thing. If I move it twice, what do I get? Okay, so it makes a solution 987. There we go. Okay, that's cool. If I go a couple more times, does it finish? Yeah, 98765, and then it fills in the board. So it can do those. Okay. So let's see if it can handle this now. So this might still be a hard problem because we're dealing with several different thermometers, but it handled this fine. So the only reason why this might be hard is that it might be that since there is enough constraint here for it to run into a lot of contradictions, that it has to do a lot of backtracking, and it might still need a heuristic. But maybe before it was so over-constrained that we were looking at an impossible case that was really hard for it to prove its impossibility. And maybe now it will be smoother. All right, so you can see it's behaving different because we used to be in a deeper guess number when it would do this. Now it is like very meticulously just chopping through variables, 41, 48, 51, backtracking and trying them again. Is it making good progress though? Does it have any chance of finishing? Well, it's pretty deep into its guess list at this point. Its guess numbers getting high. And yeah, these learned clauses are getting pretty long. That's like about 100 elements. About 200 elements. I don't know. I don't think it's moving towards a solution still. It's curious because it doesn't struggle so much with just one of them, but when it's looking for one little solution in the pack, and the way it has to get there is through this style of deduction, it seems to struggle. It seems to struggle to think its way through the thermometers the same way it could with the Sudoku constraints. Right? It's not as good at this. And I'm curious why, but I'm not sure how I would study that today. So I'm not going to expect a solution to come out. I think we'll get to 500 or 50,000 lines here. Then I'll stop. I just want to see. I'm very curious to see if it looks like it's making progress. Like if I ran this overnight, would it work? It's now in the range of like guessing this 200th variable, the 300th variable. At the beginning, hey, look, it could be making progress. That could be that's about a third of the way through it. Let's do this. Let's kill the one that's running in forcoder, because forcoder slows down anything that is printing. And let's pop in here, turn back on that piece of the log there, but then I'm going to turn off Yeah, I'm going to turn off logging altogether in this range. And switch these off with printfs. Okay, I'm going to build it. I'm actually going to go into my local variables here and switch this to release mode so it'll build an optimized version. And then we'll pop in right here and let that run right there. I'll give that a few minutes and see if it can do it. And in the meantime, I want to go here and make some more notes on my to-dos. Right, so we need to build better guess heuristics. It's not done yet. Let's see, what else can I do on this? Let's see. Priority queue, I would want highest impact variable or something like that. We might also want to talk about like thermo Sudoku heuristic. Can we build special heuristic, a special heuristic that'll get it through this issue here? want to do the river crossing solver, and we want to do maybe like a crypto problem. The meow hash, maybe we could do it. We could recreate the analysis of the meow hash article that used a SAT solver and see how that goes. Let's see. Watchers does the propagation, learned clause simplification, learned clause removal. The heuristic does better, faster guessing. Trying to think. Yeah, I think this is a pretty good to-do list. Based on what we've got here. I mean, there's a lot more to do, but it's also starting to feel like the project is over the hump. The rest of this is tweaking it to death, making it this is a pretty key thing. We need to find some better test cases to really expose this this kind of the need for this, but we might also be able to make just general Sudoku specific heuristics. Like I'm thinking it works so well on basic Sudoku that it doesn't feel necessary, but there is sort of a strangeness about how it makes its guesses right now that maybe you could just go like, well, if we know it's a Sudoku problem, how would we make our guesses? And we could think about like user supplied heuristics or something like that, where the user of the SAT solver kind of knows the structure of their problem in a way that lets them make guesses that are way better. got the clause learner from Minisat. Was there anything else from Minisat that was not super major stuff? I've kind of got it all. I think the other biggest one would be, this is also actually more of a heuristics thing, but these are not guess heuristics. What was the other? Oh yeah, just like the low level stuff. We could definitely spend some time trying to figure out how to max out the speed on that. I guess I'll move this here, and then we want another thing we could do at the solver feature level is we could do a reset, and we could do a phase saving thing. Reset is when you go back to the beginning. So after a certain number of conflicts, you say, hey, you know what? I've had a lot of conflicts. I'm going to go back to the beginning and start from scratch and start from somewhere else. And that way I can, you know, start learning about a different part of the problem and maybe crack it open from a different angle. But when you reset, you don't lose your learned clauses. So you unset all the various assignments, but you keep the learned clauses with you, which is sort of the more important meta progress. And then you start from somewhere else in the problem space to explore and find better learned, higher quality learned clauses faster. It's kind of the thinking. And then phase saving is the idea that when you backtrack and lose some of your guesses, it can be valuable to remember which guesses you had made and reuse those, because if there's not if you're coming to the point where you're trying to make a guess, instead of running your heuristic again, if your guess from before is valid in the current context, then you can just keep reusing it. So if you do a backtrack, you lose some part of the stuff you guessed you aren't doing. Some of the rest of it, you might as well keep using it. So like keep the heuristic work that was already done, because the heuristics to analyze which variables should go next might have done some work, right? That might not be free to calculate what to do next, especially in things like the narrow clauses method or in a user supplied heuristic. So it might be good to just have built-in phase saving, which says like, well, if you've already made guesses before and they're still valid, but they're not currently active, let's reapply them before we ask the heuristic to generate new ones. Right, so some other stuff we could do is over here in the land of usage features, we could have a simplify SAT formula with fixed variables kind of thing. We probably want to do more research onto the pre-processing problem. All right, I think that is good. K Monk asks, "Hey Alan, do you find it difficult to work consistently on researchy side projects like this while doing a full-time programming job well?" Let me think about that. Um, I think the answer is yes. Um, I think that if you have a full-time job that is not researchy, it's not sort of research style work at your full-time job, then well, I just don't really know what those kinds of jobs are like. My programming jobs have always been closer to researchy. I've done like some production work on the stuff I do, but I'm usually the early side of the production work, doing the research to sort out what all needs to happen, and not doing the main like cranking through to-do list stuff. So since those are the jobs I've had, I've always felt like if I'm doing that for work, it becomes harder to do it off of work too. I don't know if that would be the same. It might just be in general that full-time jobs are destructive of your sort of focus battery, right? Your attention battery. They I don't know. I have a lot of thoughts on full-time jobs and work culture and stuff in general, which a lot of this gets mixed up in. And I think the general answer I have for you, though, is yes. Just in case you didn't know, I don't have a full-time job right now. So, I'm doing all this now because I have left my full-time job that I had last year because I wanted to do a lot more of this. So, basically, I do find it difficult and had to rearrange things in order to make more time for this. Um, so if you are working a job and finding it difficult, I would not beat yourself up over that or anything. Uh, that is pretty typical. Yeah, Indiener is talking about the cycle of having spare energy for side projects and then burning out on them. Um, yeah, K Monk. Look, I when I worked full time, I got progressively more and more depressed because I felt like I had less and less ability to set aside time for this kind of stuff, and vice versa. Or the depression was making me feel like I couldn't do this anymore. I don't know which was the chicken and which was the egg in this situation, but they definitely were sort of, the time I was spending at work and the feeling sad because I didn't have time for this was making it hard to find time for this. And they were then making it feel like I was more sad and had less time for this and needed to put a larger proportion of my time into work. And I don't know. Um, it also really depends on the details of your job. Full-time programming job can be a lot of different things. If full-time programming job means 40 hours of sitting at your computer every week, then you're already being tortured, as far as I'm concerned. And you should definitely be taking your time off from work to get away from the computer. I mean, I've spent 5 hours streaming today, and 5 hours is far more than how much I normally like to be at my computer on a day. Um, yeah, I don't know. If you want to do good research work, you need to have lots of time away from the computer to like reset your brain. Clear minds do better research. And unless you have a full-time programming job that is also permissive of you doing stuff outside of work, sharing what you're doing. If you're doing research and you're not allowed to share it, it kind of feels pointless. So how much you're allowed to share and how much friction your job adds to the process of sharing what you're doing, those are factors that matter. So I don't know. It's not a simple question, but I think the general answer is yeah, it's pretty hard to have a full-time job and do something like what I'm doing right now. Not that it can't be done, and I have done stuff like that before, but like I've not gone this hard on a SAT solver before I quit my job because it was really hard to do that. And it would have probably pushed me into further burnout. But I want I do like now have lots of simultaneous projects. Like I work on SAT solver, I work on the story engine, I work on organizing low level details in my code base, like the dynamic linking features that I'm working on. And so having multiple things going on isn't a problem for me. I've not found that that's a problem. It's not a problem to have multiple things. It's a problem. There's other factors about what a full-time programming job usually means that seem more the issue, like the 40-hour a week sitting at the computer assumption. That seems like a bad way to do lots of high-quality programming to me. I think you maximize your high-quality programming at somewhere around 15 to 25 hours a week, probably. At least in my experience. Anyway, yeah, I'm going to wrap up for today. Let's do one more check. Yeah, I'm going to keep letting that run in the background, maybe come back in a few hours and see if it ever finishes. Because I'm curious, but it certainly, we found a hard problem for it, and we'll dig into that more next time, probably working on the guess heuristics and the optimizations, see if we can get it to solve this thing. But for now, we're going to call this good. Wizard of Datums, how do I like to spend my time away from the computer? So I don't have a great answer for that. Like I spend a lot of time outside, like walking and listening either to talks or just to nothing, like to the world, to the sounds of the world, to get my brain. But the walking is the more important part. It like to get back to like a clean slate set of like mindset, if that makes sense. I don't think stress makes for a very good creative thinking or problem solving mindset, and so spending enough time programming and pushing yourself to the point that you get stressed is counterproductive. And I do the walking I do something like that to unwind the stress. I find it difficult personally. I have a hard time finding ways to unwind stress once it's there. So it takes me a lot of time. And there's a lot like I can't play video games or watch TV or do a board game night to reduce my stress. None of these things seem to make any difference. They kind of just pause my stress levels. Sitting down and reading or like studying math or science helps my stress levels sometimes, but it can also be difficult to get into that mindset. So I don't know, stuff like this. Well, okay, Monk, I hope that your projects have been fulfilling, and hopefully they become successful. But if you do run out of money and have to get a job, I'm facing that too. At some point, I will not be able to do this forever. I have plans in the work for taking things I'm doing and making them just self-sustaining, hopefully. Although I have to admit, I am loath to spend time on the details. The reason those aren't out the reason those parts of my project aren't out are really because they involve things like web programming, payment processing, um, things like this that I am loath to spend time on. And I'm trying to just stay in a space where I can enjoy what I'm doing most of the time. So hopefully soon I can start testing out a business model to make this sort of research stuff self-sustaining and see if it works. But it's not nearly as much fun as what we did today, for instance. Anyway, as I am wrapping up, let me give you all again some pointers to places you can go to follow this project and other projects. So, MrForth.com. If you're on the newsletter, you will get updates when big things come out, when articles come out, and when if you depending on when you sign in, you can set some features. You can sign up to get notifications for my podcast episodes. We just had a new podcast episode come out earlier this week. Visual programming, kind of interesting if you want to check that out. And you can also come over here and you'll see all my different, we can go into any one of these. There's, example programs and stuff. And I have more of these coming, more code coming to the Mr. Forth Git. So you can check out my open source projects that are available right now and stuff like that. So take a look at that if any of that is interesting to you. And otherwise, I will see you all around the internet. Bye.